Okay, thank you. The pointer is this one. Where were we? Yeah. So defining proxies are difficult, or identifying proxies are difficult. And not only that, you have to also calibrate them. You need to know in what ranges they work, whether they work in entire time period of geologic history, in all kinds of climatic or systems or not. So there are so many things I'll touch upon a little bit. So I assumed that a lot of these would have been told to you. I do not know how much were covered in the first day. Naveen asked me to cover the chemical proxies, particularly how geochemistry can be useful, because I am a geochemist, so that I claim. So some amount of work I have done. So which I will tell you that climate, past climate doesn't necessarily mean climate of quaternary. This is what we probably have been told, or maybe this is what most people work on, like last couple of million years or 2.5 million years. But look at the Earth's history, the climate would have been there as long as the atmosphere has been there. So atmosphere system came into existence very long time back. So we do have a climate system to study for the entire, almost the entire history of the Earth. Some pictures I have shown you, but I'll focus more on chemical proxies. So these are something which you already probably know. These are some of the proxies, like tree rings, bars. So wherever you can have some records of climatic variables, like temperature, pressure, wind, humidity, and if you have a resolution, like every year they have recorded that information. So these are some of these things where you can extract the information in the past. Of course, it's not straightforward, but we can do that. And there are some pictures, of course, it's unreadable. I'll show you better pictures, where some chemical, so periodic table has 92 elements. Okay. So every element can be tried and seen whether it can actually act as a proxy, whether it can record some climatic information or not. If not as an individual element, whether like group of elements or ratios of elements. So these things have to be studied and understood in the past, because we need some kind of proxy in order to understand past climatic variables and how it has changed. So some examples are shown here, but I'll come back to it again. Okay, some basics, just for completeness, for me and as well as you. So what we call a climate is basically nothing but a long-term, why it is
cursor. So you move, it will move.
That is moving, but it is not moving the way I want it to move. It is going really slow. All right, so it is controlled through this, I guess. All right, so climate is the long-term pattern of weather in a particular area. So let's say we say Pune climate, or let's say Maharashtra's climate. So it will be an average climate, average weather over a period of 30 years. Regions, so basically 30 years is what most climatologists would say, that a 30-year average of the weather system, we can call it a climate. So climate of that region. However, it can also vary depending on how you define. So if you go back in time for millions of years, billions of years, it will be very difficult to have 30-year resolution. So you will combine it for millions of years maybe, or thousands of years. All right, so what are the parameters which we can actually use to define a climate system? So there are some here, there are many. These are the major ones which I understand are essential to know what kind of climate we are living in, or what kind of climate you can define for the past. Solar radiation, obviously, sun is very much part of the energy system we have. And atmosphere is continuously bombarded with sun activity as well as the radiation that goes back. So solar radiation and sun's behavior, Earth's behavior itself also, like you have Earth's rotation, revolution, its axis, etc. They all control climate. So I have put them in solar radiation, how it varies. So that is a parameter. Temperature, of course, this is the most important thing and most common thing people try to estimate as a part or climate variable. You say temperature is 50 degree or 30 degree, that defines some kind of climate system. Of course, humidity, precipitation, rainfall. For a country like us, we define climate in terms of rainfall, isn't it? Monsoon is everything for us. So therefore, precipitation defining the climate system in Southeast Asia is very important. So even if when you study the past climate, we always try to focus in one of these two things where rainfall or precipitation is one of the important factors. We want to know how was the rainfall in the past. That will define the climate of that region going back in time. Of course, then you have pressure and wind, etc. So these are certain parameters which can be traced back in time. Okay, I'm a geologist by profession. So whenever I talk about climate, I go back to the day one. So I don't know how many, probably a lot of you are from our science background. That's the geologic time scale. Okay. So just some important events are listed. It's a picture taken from somewhere. So 4.6 or 4600 million years ago, Earth being came into Earth like planet, or solar system evolution started. And then here we are. So these are the major eons, eras, and periods. They are listed. Don't worry about that. Certain important events are listed here, particularly in terms of evolution of life. Now, does it really matter what life? Life and climate, they have always been related. Change in life always dependent on, or evolution of life kind of been triggered and became extinct depending on the climate or even extreme climates. So, this is, I'm not very happy with this. So, do you have a pointer? I'll try again until then. So some important events I have listed in terms of what you can immediately gather as climate change. There have been glacial events, like in modern times, or let's say last quaternary period, we had ice ages. Similarly, in the past, Earth as a whole had observed or have undergone severe glacial event, low temperature, extremely low temperatures were there observed in ocean. At one point of time, people believe, particularly during this period, it's called cryogenian, around 722, 635 million years ago, entire Earth would have frozen. This is what people believe, and they call it the snowball Earth. So all oceans of Earth, or let's say glaciers, had come down all the way to equator. So you can imagine what kind of conditions are there. So it's a climate change, but long back in time. And life evolution, as I told you, they are closely associated with such events. For example, after this glaciation event, we call it Neoproterozoic glacial events. After that, there was sudden emergence of life, particularly animal life. So are they related? We are still trying to understand. So these blue color marks here are the major glaciations I have marked. One is, of course, the past glaciation, which people might have told you about the ice ages, last ice ages, last glacial maximum in Quaternary. Okay, so how do we know all this? So we would have used certain parameters or certain proxies of climate. How do we know that temperature was so low? You need to freeze the ocean, so temperature should have been below -10 or -20. How do we know it? So we would have extracted this information from some record. So what is that record? So I'll touch upon it sometime during the course of this talk. So there is another picture just to impress upon you. Temperature, as I told you, is the most important atmospheric or let's say climate parameter everybody wants to measure. So you have multiple proxies for temperature, like to estimate past temperature. So people have tried, so a lot of proxies have been used here, okay? to estimate the temperature in the past. So whenever you say global temperature, it's very difficult to measure the temperature of the planet as a whole. Today we do have modern day we can do that. So earlier either you estimate temperature of that particular local or the particular region, or you estimate the temperature of sea surface. We call it SST. That is much easier to estimate than estimating the global temperature. So SST or sea surface temperature has beautiful proxies. I will explain a couple of them, which can take you back much in time. So up to 500 million years, you can see people have actually estimated the sea surface temperature. So based on that, they have estimated what would have been the Earth's temperature and when it would have been warm, when it would have been cool. Okay, so it's going from here all the way to there. So the global warming, we are talking about the future, it's here. So it's warming because we are still actually in the cooler period of the Earth's history, if you look at the entire history. However, it is rising very fast. That is what is alarming. Okay. So these red ones are the high temperature. So you can imagine it had gone to higher, like 90 degree Fahrenheit all the way. I mean, so these are the main important events. I don't know how many of you know. There was something called Paleocene thermal maximum. Around 50 million years ago, the Earth's temperature as a whole was very high. Okay, so it is, see, so if you reach that stage, probably we'll all go extinct. But Earth did have that kind of temperature in the past. All right. Before I get into explaining how geochemistry can be useful in understanding past climate, I would like you people to think about these things. Okay, younger guys will take up research at some point of time. This is something not entirely mine, taken from other people's ideas, but I have been closely associated with some of these problems. So I would like you to think about it. Maybe new ideas can come up. There are many interesting problems. The most interesting one for me, there is something called the faint young sun. Okay, so after Earth evolved, let's say 4.6 billion years ago, Sun was also evolving because solar system, entire solar system formed at the same point of time with a little gap of few million years here and there. The Sun was very young. So if you know a little bit of physics, or if you know what you call astronomy or formation of stars, our Sun basically initially started with entire hydrogen. So then hydrogen bonds into helium, then helium bonds into further. Like that, higher elements are produced. We call it nucleosynthesis. Nonetheless, so initially it would have been all hydrogen burning into helium. So that process is a very slow process. So the young sun would have been very faint. People believe means if you do the calculations, you will realize that during the first 400, 300, 400 million years of Earth's history, sun would have been very faint. Okay, all the way coming to Archean also, if you know, around let's say 4 to 3 billion years, let's say, it would have been very faint. So if it was faint sun, then everything should have been frozen. But Earth has no record of freezing during the initial period of time. In fact, it was very hot. So there is a dichotomy here, or let's say there is a paradox here. Sun was so faint, even then Earth was very hot. So what happened? And what happened to life? We do see stromatolites, etc. But we don't really know what happened during this period. There is something called long-term homeostasis. I don't know. I don't want to get you in that. For long term, some life remains as it's like an equilibrium. Nothing, no evolution happens. Then suddenly they will live on. But for a long time, they remain like that. So this is a very interesting problem. The problem is we are not able to solve this because we do not have proper records. We are talking about first 500 million years, let's say, or first billion years. The records are very few and mostly altered. It's very difficult, but it's a very interesting problem. Somebody may try to understand what happened. There are theories. They say we had a lot of CO2, so global warming was there. Therefore, Earth did not freeze when it should have. So there are hypotheses, but There is no theory yet as such which can explain. Same way, oxygenation of oceans and atmosphere. Probably you all know that the oxygen we have today was not like that in the beginning of the Earth. In fact, we didn't have much oxygen, or maybe nothing. But something happened. People believe, or we have records to show, again, using proxies, that around 2.3 billion years ago, there was a big oxygenation event. A lot of oxygen came into atmosphere, almost 70% of what we have today. And then ocean oxygenation also happened because you need, we have evolution of life in the oceans also, they need oxygen. So prior to that, most of your animals were anaerobic. They didn't require oxygen. So therefore, the evolution would not have happened much faster. But after oxygenation, there was evolution of animals, plants, and land plants, and all that. And then here we are. Similarly, there are other interesting problems, like you have glaciations, as I just hinted you, snowball earth problem. We are still trying to understand. We know that it existed. We do not know why it happened, and we don't also know how Earth came out of it. So if everything was frozen at one point of time or several points of time, then how did Earth come out of it? So we have to think about that and find evidence for that. Same way, mass extinctions. All these geological boundaries I showed you, most of them are actually marked through fossil discoveries, or rather, it's based on biological evolution. Many of these boundaries have basically are marked along which or during which a lot of life form got extinct. So we call them mass extinctions. Some of these mass extinctions are internally kind of designed or internally happened within the system. Some of it is because of impacts, etc. So some of them we know, like our KT boundary or Cretaceous Tertiary boundary, or when dinosaurs went extinct. It is kind of established. We had a massive asteroid impact, and of course, at the same time, we had volcanic eruptions here. Right, we are standing here, and both could have triggered this extinction event at 65, 66 million years ago. Similarly, there have been many, many extinctions. Should I worry about it? Yes, because how it would have changed the climate, and ultimately it would have affected the life through the climate, not directly killing them. The climate, let's say the theory is that at KT, the entire Earth was covered with the dust which came out of the asteroid impact, and it would have kind of no solar irradiation would have penetrated all the dust. So it would have been a cooling period for after a long time, for a long time. So it would have ultimately killed life form. So there are many theories, but we need hard evidence through this kind of climate proxies. The same way, there are other things, and something which you may like, or some people like to study, climate and human evolution. Humans came only, let's say, or hominids came only last 4 million years of Earth's history. But we have evolved into very different people than what we started. And then we have civilizations which got lost. So did climate affect them? Or what happened to them? Why all these civilizations vanished? If there is climate was a factor, we need to study. So therefore, studying the paleoclimate. You cannot study it directly, you need a proxies to study. All right, so these are some interesting questions you may think and try to, if you take up studying climate, then you may want to look into this. Okay, now defining the proxies. So the proxies, I kind of explained you, they can be physical proxies, like I have listed here, texture, structure. So if you are looking at sediments, let's say, sediment grain size can also give you some idea about the climate system. It could be arid, it's a wet climate. So they're very crude, but nonetheless, people do rely on it. So they can be physical proxies. Then you have chemical proxies, which I'll talk about it. So like isotopes, I think yesterday you had a talk on isotopes, how stable isotopes of lighter elements like carbon, oxygen, nitrogen, etc. can be utilized as proxies of past climate. Similarly, I'll touch upon some of the elements which can be used to understand some climate variables in the past. And there are biomarkers, like organic molecules are there, and different life forms have different molecules. They can also give us some idea about the past climate. And then, of course, biological, it's a lot of that we have an institute dedicated to it, BSIP. They work on pollen, spores, etc. So they are climatic proxies based on biology. Okay. All right. However, again, to make sure that proxy works, you have to make sure that it works in the modern world itself. For example, you are measuring, let's say, direct measurement of temperature. It's a thermometer, let's say. Even that is not direct, but you measure, it is calibrated properly. You measure the temperature of a particular place. Now you want a proxy. Let's say I say delta 13C of or delta 18 of calcite can be a proxy of temperature, stable isotope, let's say. So first you have to establish that is indeed that it can give you temperature. So what do? You have to design an experiment where you fix the temperature of your water, grow calcite there experimentally, and measure that. You take that calcite out, extract the oxygen out of it, measure delta 18, and see that whether it gives you back the temperature at which you have crystallized the calcite. So that is how we establish the proxy. I will show you how people do when they go back in the past. So every proxy that will be called a proxy if it is properly calibrated. But it becomes very difficult when you go back in time because the modern day counterparts may not be available. So it is like you have to rely on a lot of assumptions. It's difficult, but doable. Some I have listed. I will be focusing more on chemical proxies. So temperature, as I told you, global temperature going back in time will be difficult. The only thing we can really estimate with confidence is the sea surface temperature, or SST. So there are many proxies people have used. I'll give you some examples. Delta 18, you probably would have seen. I will give you one picture how delta 18 has been used, but you will have more detailed description because this is very widely used temperature proxy, okay, of paleoclimate or SST. Delta 13C, you may be surprised, but yes, we do use. Carbon isotopic composition is also utilized, of carbonates are also utilized as a proxy very indirectly of climate. Then magnesium by calcium, strontium by calcium, all these are in calcite. So why calcite? Because calcite or calcium carbonate is a chemical precipitated from water. In seawater, all these life forms you see in sea, like microorganisms, they crystallize or they have test shells. So they crystallize calcium carbonate. So the calcium comes from the water, oxygen, hydrogen, everything is there. Oxygen is coming from water, magnesium, strontium, everything is coming in from water. So it is crystallizing its test around its whatever life form in equilibrium with the seawater. So there is a direct link and it has a short lifetime. So whatever temperature on which it is actually surviving, that all these compositions in the test will be kind of a function of the temperature that you have to calibrate. It may not be direct relation. There's something called transfer functions. So you have to actually find out how exactly the relationship is. Because this is proxy, delta 18, now you have a temperature. How T and delta 18 are related. That you have to establish in modern times. Then you take it back in time. Okay, so some ocean stuff I have written here. Ocean controls climate in a big way. So if you can understand the ocean, your land records would be very few and far between. It will not be continuous. Ocean records, at least up to 66 million years, it is there. In the ocean, you take a sediment core, you have a very continuous record. You go back in time, millions of years, again, ocean sediments you can still find. So ocean will give you some idea, and oceans control the climate of the, let's say, atmosphere, chemistry also. So by studying the ocean parameters, you can understand the past climate. So there are many climatic proxies or say chemical proxies of ocean I have listed here. So I will not discuss any of these. I have just listed here. Same way, atmospheric CO2. Suppose you want to know the level of atmospheric CO2, there are some proxies like boron isotope, delta 13 carbonate, or organic matter. They have been used quite widely. Same way, you can also kind of indirectly understand level of CO2 in the atmosphere by studying some proxies for chemical weathering. So I don't know how many of you know, a rock particularly weathers chemically, every mineral will break down. So how do they break down? The CO2 in the atmosphere, when rainfall happens, it actually gets dissolved into the water. It forms carbonate or bicarbonate, carbonic acids, you can say S2CO3. So that will actually, when you, most of the rocks, let's say, are silicates. Carbonate rocks will easily get dissolved, but that will not change the CO2 in the atmosphere. It may not be a proxy of CO2, but chemical weathering of silicate is. So what happens? This reaction, the rainwater carrying bicarbonate reacts with silicates, it breaks down the silicate. So in the process, finally it will get dissolved, and in the ocean there will be precipitation of carbonate. But one CO2 gets released. So one CO2 gets consumed with time. So if you can estimate, of course, the proxy is different, strontium isotope ratio, or people study CIA, I'll show you some other proxies of chemical weathering. So it's an indirect way. By knowing how much chemical weathering has happened, you can estimate atmospheric CO2. Okay, it's very tricky, but people have done it. So there are some examples of chemical proxies. So I'll touch upon a few, paleo-SST, and then I'll touch upon a new kind of proxy which I think are usable to understand past climate. I'll describe it from some of my work. Okay, delta IITM, I think you had an entire lecture yesterday. I'll just show you just how do they do it. So what is the idea? Idea is that, like I explained to you, calcium carbonate, or let's say, what is it? Delta IITM, right? So it's oxygen isotopic composition. Isotopic ratio, so by definition, it is 18O by 16O of the sample divided by 18O on 16O. It's the abundance ratio. Okay, how many atoms of 18O are there in your material? 18O, 16O, and the sample divided by the standard ratio minus 1 into 1000. So don't worry why it is like that, because it's a small number to make it a big number, and the variations are close to 1. So they have put a kind of definition like that. But this 18O by 16O abundance ratio in a carbonate, okay, changes, okay, from wherever it is taking the oxygen from, mostly from water. During that crystallization of calcite, the 18O by 16O in the water changes when it comes to the matrix of the calcite. And that change is called fractionation, isotopic fractionation. That's a function of temperature. Okay, so here we are. If you can measure the change, you actually know the temperature. So if you know the delta IITM composition of water, or sorry, calcite, you can so you have two unknowns here: delta IITM of the water and delta IITM or the temperature. These are two unknowns. What you can do, you can measure delta IITM of the calcite, which is available to you. Fortunately, since seawater is a big reservoir, so its delta IITM will not change that often unless you freeze half of the ocean or some significant amount of water. Its 18O has not changed much with time. So it is, by definition, it is 0 today. So it had remained around 0. So basically we had two unknowns. One unknown is fixed. Now the other unknown is temperature. So if you measure temperature by deducting this calcite minus water, you will be able to estimate the temperature of crystallization. Therefore, the temperature of the seawater or the SST. But as I told you, to establish a proxy, people first have to calibrate. So they grew shells in the lab or to crystallize chemical precipitates of calcite, providing calcium ions into the water. So these are the calibration lines. So more or less linear. Delta 18O of your material and temperature is kind of linear. So based on that, there are many equations actually, because this is a very widely used. And also the proxy, it's not a straightforward proxy also. It will vary depending on what kind of system you are using. For example, the same thing, delta ITNO for a calcite and for aragonite, they're all calcite, will be different. And their temperature dependence will be slightly different. So based on that, you can have an equation where you can directly, all you have to do, measure delta ITNO of calcite. Delta ITNO of water can be assumed or zero, as I told you. Or if you have another way of doing it, sometimes all these calcite matrix may preserve the water itself as a fluid enclosure. So some people can measure directly of the water from which it has precipitated. So thereby you can measure temperature. Okay, so that's how people have measured temperatures of Paleoceans, going back all the way to, let's say, 66 million years for as long as the record is available. But the calibration has to be pakka. Secondly, this delta ITNO, you have ice cores, which are basically water frozen of that time. So there also you can directly measure, and you can know the temperature of precipitation. So you will have idea of the global temperature. So there are many ways delta ITNO have been used to estimate temperature from the system from which that has been crystallized. So this is an example of SST. Similar example can be there for ice cores also, where you can know the air temperature. Okay, so I hope you already know this. There is one, I will not get into actually how temperatures are measured, but because you can measure temperature, you can correlate climate of one area with the other one area. We call it correlation, stratigraphic correlation. Suppose you raise cores, everybody is going and raising cores everywhere. So you study, you have a basically time period going back to thousands years, several thousand years, some people get millions of years. And then you measure delta ITNO of these life forms which are living, they have died and settled in the ocean. So you have delta ITNO for foraminifera, particularly planktonic foraminifera, people also use benthic foraminifera. You measure that delta ITNO. And then you correlate to it some other core or a global record. So some records are available. This is one example I have shown you. So this is the top one is a sample core which is taken, and you want to know what are these things up and down going delta ITNO variations. Is it related to climate or not? You can, if you want to directly measure the temperature, you have to go through calibration. Otherwise, you can correlate with some already existing calibration. Is another curve here, which somebody else had done. So you see, delta ITNO here had increased during this period of time around 20,000 years ago, roughly. You see, this is in our sample core. Same way, here it is done, but these are calibrated. So this is the period when we call it last glacial maximum. Around 20,000 years ago, there was a large drop in temperature on the entire Earth. And that is reflected in the drop in the temperature in the sea surface temperature, which is reflected in delta ITNO of the calcite of the foraminifera, which has crystallized from that ocean water. So what we are studying? We are studying a proxy, which is delta ITNO of a calcite test. And it is faithfully giving you the information that there was a lowering of temperature 20,000 years ago. Okay, so this is how it works. So you can actually do, even without knowing the age, you can use this as a stratigraphic tool, we call it, and find out the age of your sample. Okay, so paleotemperature is mostly what people look at. I showed you delta ITNO. There is another proxy because the calcite matrix itself has magnesium. Okay, so if you magnesium can replace. So what else you can have? You can have cadmium, barium, strontium. All these, because they have similar charge and ionic radius like calcium, they can replace the calcite matrix. So this replacement, it is not a random replacement. This is thermodynamically controlled. So once I say thermodynamics, means temperature is there. If you are smart enough, you can also calibrate this and extract information about temperature by measuring just magnesium by calcium. You don't need a sophisticated mass spectrometer to measure delta ITNO. You can measure magnesium and calcium and still find the temperature, paleotemperature of the system from where that particular thing has come. So that is the principle. And of course, I will show you a calibration curve. This calibration is not linear. Okay, people have seen. So these are again mostly planktonic foraminifera which live on the sea surface. So this was an experimental carried out, or like we call it, a sediment trap was done in Bermuda. So you can see these are basically foraminifers. There are surface dwellings of foraminifers. We want SST, so you want to deal with surface animals. And if you see the magnesium by calcium ratio in them, and you need temperature, so the temperature they calibrated with a delta ITNO. Delta ITNO directly can also give you temperature. So that calibration, temperature measured through delta ITNO, and this gives you a relationship. And that is this kind of relationship. It is not linear, it's an exponential relationship. So it is kind of a studies, and it works very well. So Mg by calcium, if you can measure very accurately and precisely, you should be able to measure temperature of that system, or particularly the sea surface temperature of that period which you are looking at. Okay. So it's a calibration because it's the modern day. So in the modern day, you study this, then you go back in time, use the relationship, find the temperature. All right. Some application, I just want to show you how perfectly it works. So this is work in 2017. So this is actually sea surface temperature derived from magnesium by calcium, the last panel, and this is based on delta ITNO. So you can see it's almost 1-to-1 match. So yes, magnesium by calcium is also another elemental proxy for paleo temperature. Okay, so there's another one, because as long as you have the matrix available to you, you have different elements replacing calcium, and their replacement is temperature dependent, you can use it. So strontium by calcium is another example. It is not very widely popular yet. The strontium concentrations are very low, and you need to measure it very accurately. So you need probably isotope dilution measurements in thermal ionization mass spectrometry. It's a little bit tricky. Nonetheless, it's a beautiful technique. And some examples are there. So this is, again, the calibration here is kind of linear. And then people have used and seen in corals particularly. So here, basically, some of them are measurements, some of them are through this calibration. The calibrations are linear. That means the temperature and strontium replacement is a linear relationship. And thereby you can measure. So you don't need to do isotope. You can do this and still find SST, a paleo SST. All right. This is something which you may not have been told. Carbon isotope, can it be utilized as a paleo temperature proxy? For me, yes. It's not exactly finding out temperature. We indirectly find out how we do it, or what is the purpose. So now I'm expanding my time span from modern quaternary times, going back in time. All these I showed you, magnesium by calcium, delta ITNO, they're extremely difficult to use when you go back in time. First of all, we do not have foraminifera, much of it beyond 66 million years. Because why I 66 I'm saying? Because the modern, if you take a core, at some places you may get up to maybe 200 million years, because that is the oldest ocean floor available to us today. But most of the time you don't have sediments going back in time like that. So best is around 70 million years you may get. But that is still not, 10% of Earth's, or let's say 20% of Earth's history. So we have more than 80% is still unknown to us. So you study marine record, marine sediments or marine carbonates. But then these things get altered, because all these geologists will know there is something called rock formation process. They change the rock, make it hard rock, we call diagenesis. So entire composition changes. So it's still very difficult to extract the temperature information directly the way we did using foraminifera. So here you have to rely on different smart ways of getting the information indirectly. So one such example is delta 13C. Now how does it work? So do you see this black thing? That's the delta 13C record of carbonates going back in time from 0 to 4 billion years almost. You see, it's kind of flat, but you must see these things. Okay. Now, carbon, an element which is taken by biology mostly, and also calcite. So there are two reservoirs which take carbon, and carbon has two isotopes. I'm not talking about 14C. You will hear it afterwards. 14C radioactive has short half-life. In geological times, it's irrelevant. So 13 and 12, that ratio fractionates. That fractionation happens. There are two systems which take it. One is your organic matter, biology. Another is carbonate. So when Earth started, there was only CO2, let's say. That CO2 would have come from Earth's interior, which is mantle. So it had a composition, or has a composition around -5 per mil. We explain it at per thousand or per mil. So this 5. So that's our primordial. Then it is distributed between organic matter and carbonate, or inorganic matter, inorganic carbonate. Organic average composition is -25. Assuming the way they fractionate between carbonate and organic has not changed with time, you can actually measure delta 13C of carbonate and find out this F value, that amount of organic matter. Okay. Now, organic matter means life. Now, it has been observed. First, some calibration has to be done. Whenever delta 13C, or let's say biology was thriving, a lot of organic matter is there. So -25 into a large number, delta 13C becomes negative. Okay. Same way, if you have less life form, okay, the F becomes very small, this becomes, or just immediately after. So you can calculate and find out how much of your F organic matter is there, how much of bio, we call it productivity, because mostly it is marine, so marine productivity. So it's indirect, okay, how temperature information is gathered from here. Okay, I would like to show you these peaks. Okay, these are negative delta 13C variations. So let us not worry about right now delta 33 sulfur. Look at delta 13C, this black curve. So there are some dips, you see. So there are negative excursions. Okay, so this delta 13C becomes very negative when F value becomes what? Higher or lower? Okay, so you would think it just happens just prior to that. Okay, you have to go, okay, maybe I'll go with this first. Delta 13C becomes positive, highly positive. Delta 13C of, what is this? This is carbonate delta 13C. So if I revert this equation, delta 13C of carbonates becomes positive. To make this positive, the F value has to be what? This has to be positive. So it will be negative. This F value should actually be very high. Then only it will become positive. You have to take it to the other side. No? -5, let's say it is 0. This is delta 13C will be -5 if F is 0. If F is very large, delta 13C will be highly positive. So this is when the biology thrived all of a sudden, around 2.3 billion years ago. So that is what we call it great oxygenation event. Independent proxies shows there are a lot of oxygen in the atmosphere. People then started using delta 13C as a proxy of lot of oxygen. Okay, it's not a temperature proxy yet. I'll come to temperature. So nonetheless, it's a climate proxy, lot of CO2. We call it great oxygenation event, 2.3 billion years ago. So that delta 13C peak you see. So just revert this logic. Whenever it goes down, that means the AF is very small. So when AF is small, that means you have less, we call it organic matter burial, because it has to be buried, taken out of the system. So AF is very small. That means something happened, life form vanished. So it is established, calibration wise, all these represent large scale glaciations. In ocean, when temperature goes down, biological productivity goes down. Life basically doesn't exist anymore in the way it was existing just prior to it. So carbon available becomes very negative. and that is reflected in the delta 13C of the carbonate. So all these negative excursions of delta 13C of carbonate is a bit tricky. If you make equations, you will find out. They represent glacial events, lowering of global temperatures. So indirectly, we people who study much older formations, where these other proxies are not available, we use delta 13C of carbonates as a proxy of large-scale global temperature decrease or glaciations. Okay, so just one example. And delta 33S, sulfur isotopes, I have just given you some studies that was in the same picture. It's a climate related. They give you about the oxygen. When oxygen so came and they're studying anoxic environment, try to estimate how much oxygen was there in the atmosphere. We will not discuss that too much. Oh, I explained it, but here, okay, it would have been easier here. The same thing what I explained, I have put it here. Delta 13C of the ocean is same as delta 13C of the carbonate. This is, you start with that assumption. This is the equation I showed you. So the fluctuations of F, that value amount of organic matter, burial, results in the variation of the carbonate. Because carbonate is what varies. Organic matter delta 13C kind of fixed in the ocean. So therefore, global glaciations have low organic carbon burial. No. Yeah, I mean basically low organic matter, also low organic carbon burial, negative excursion. So these are the negative excursions. They have been identified as glaciations. So particularly these three you see, they are called cryogenian glaciations, neoproterozoic, between 720 million years to 635 million years. There are three global glaciations. One of them is believed to have frozen the entire Earth. So indirect way of finding temperature. Okay, so now I've taken a lot of time. I'll quickly end with a different way of looking at climate proxies. So if you don't have direct proxies, can you actually predict or understand the monsoon system in the past? People, they say one of the interesting questions in Indian paleoclimate science is to know when did the monsoon system today we know about, summer monsoon or southwest monsoon we call it, when actually it got established, at what point of time. So there are many information, many theories, hypotheses, I should say. Mostly it is linked to the formation of Himalayas. That is the current belief, understanding. So because Himalaya came into existence, Tibetan plateau came into existence. So you have a differential heating between ocean and land, and therefore change of wind patterns happens during July to September. And because of that, you have monsoon winds bringing in moisture and bringing it. We want to know when it actually started, because Indian land mass was not here, it was further down south. So we know around 655 million years ago, it actually came into existence in the way we know it today. So is it the 55 million when monsoons actually got established? Some people believe it's around 25 million years. Some people believe 8 million years. So I don't know. There are many theories to it. So we try to work on it in a different way. So in that, you need proxies of monsoon. So how do you establish going back in time? So we went for a sediment record. Okay. So there are many ways of studying it. This is not the best way, but because I have done it, I would like to tell you it is doable using rudimentary techniques as well. When you go back in time, records are very few, and we don't know where to get those records. So here we relied on sediment records. So what is the logic? If there had been monsoon, it would have eroded Himalayas. It would have put those sediments somewhere, most likely in Bay of Bengal. So we have a record in Bay of Bengal, going back in time. And if you study them, whether you can have some proxies, we can link the monsoon or evolution of the monsoon with that. Our record can tell us about when actually it started. So what we did, if you take a core, you may not get that old sediments, but nature has given us these sediments now exposed on the Andaman Islands, going back in time almost 55 million years. So these are turbidites and deposited. There are some names, geological names, don't worry. So these are these sediments which are now lithified, but become rocks. So they are exposed on the Andaman Islands because of the tectonics. So if you study these rocks, can we understand the monsoon? How do you understand monsoon? The logic is, I think I have a picture. No. Yeah. So the logic is this. So we have some isotopic composition of the rocks, strontium and neodymium isotopic composition. So these are radiogenic isotopes. I am trying to use it as a climate proxy. So these are the compositions you just see. One left hand side is the two numbers are there. Strontium isotope ratio, neodymium isotope ratio of the rocks present today on this part of the country and also the subcontinent. So if the weather, if a rainfall, erosion, rivers carry these sediment sand, they will deposit in Bay of Bengal, all over the place, of course. You study their isotopic composition and the change of the isotopic composition through time. So how it will work? So if you see, these are the isotopic composition in different Himalayan rocks, lower, lesser Himalaya, higher Himalaya, trans Himalaya. Let's not worry about that. Some compositions are there. And the idea is, if they have come, they're deposited here. Today they are exposed here. So we take material of the field, the sand, and measure their strontium neodymium composition. And we try to establish the source of the sediment. That's the proxy. So I call it sediment provenance as a proxy of monsoon. So how it works? Let's see. So up to 55 or 35, these are all sediments derived from some other rocks, local rocks, you can say. There is not much change. These first two panels you should concentrate, strontium, neodymium isotope composition. There are other proxies also. Let's not worry. So after 35 million years, this isotopic composition of strontium starts to increase. Neodymium isotopic composition starts to decrease. And this decrease is significant. So if you see from somewhere here, neodymium composition, these are the orange dots which I am talking about. They have come and become very radiogenic in strontium, less radiogenic in neodymium. And where do you have this material? If you look here, those materials primarily come from the continent. So I have another picture here. So it would have been roughly around this period, 34, 35 million years ago. India would have been located something like this. This was closing. So this is tectonics. But how climate information we are trying to gather? We have sediments of this period giving us an indication. We had a lot of material started suddenly coming from Himalayas. Himalayan mountain belt. So there would have been rivers carrying all this. So it has two ways of interpretation. One is, that means you had some river system, but the river system can only flow if you have enough water and carry these sediments all the way to Andaman Basin, where we are looking at. So that means you need really good amount of rainfall in order to carry Himalayan material all the way down, which is happening today. Does it mean we have monsoon? Probably yes, because that is what India International Ocean Discovery Program want to drill in Andaman Basin, try to figure out when did the monsoon actually get initiated based on this kind of proxies. So here we have, of course, it's not very robust because the record is not really continuous. Nonetheless, it gives an idea. Probably around 35 million years ago, we already had monsoon. Now, whether it got established at that point of time, that is yet to be established. So the bottom line is, yes, we can actually understand using various this kind of isotopic proxies, elemental proxies about monsoon as well. Okay, so I gave some flavor of how elements and isotopes can be utilized as proxies of past climate. So whether we are heading for this, we call it warm earth, or we are heading for a cool earth, it's you people to find out. Thank you. Okay.
Questions?
Can we So can we use modules which are format also for alcohol?
Nodules, so manganese nodules. Oh, iron manganese nodules. For proxy for what? Climate. Well, it's not very straightforward. Yes, it goes back in time 2 million years. Few million years ago.
You can find out because bottom they find the nodules which have gone to something few tens of millions of years. So they can give you an idea about where this is, but they tell you mostly about the ocean.
So yeah, paleoceanography, yes, but there is one interesting, not the nodule, the manganese crust nodule also can give you much more different kind of idea about the solar irradiance for that matter, because there are certain isotopes you can study beryllium-10 isotope variation in them. You can actually know, I don't know whether you know, beryllium-10 is produced in the atmosphere by cosmic rays. Okay. Now, galactic cosmic ray variation happens or can change because of solar, change in solar activity. So, more or less galactic cosmic rays will result in more or less beryllium-10 production. That can be recorded by manganese crust, and therefore you can actually tell if there was a supernova explosion, cloud cover, I don't know, large scale. Yes, I mean, there are other proxies for other things. Climate proxies, I have not seen anybody directly using. Oceanographic proxies, yes, you can know where from the iron is coming, manganese, etc. In the past, how much concentration, there are circulation, ocean circulation.
Good morning, sir. Sanjeev Tiwari here from Pune University. Sir, actually, I was intrigued by the idea. I was going through some papers. So, in that paper, the scientists from America, they were exploring ideas. I think it is there for some time that the volcanic eruptions that happen, because of that, the gases that what you were calling about the dust that we have, volcanic dust that we have. So, how you are using, how the scientists are using that dust as a proxy, like people like you are using the sediments and everything to know about the temperature and everything about the climate. So, what are your ideas about that? How we can use the volcanic dust that are available?
As a climate proxy. Okay, see, we have not established yet, but there are indications it can be used depending on their dispersion. One best example is we call it Toba ash. There is something called young Toba ash. 74,000 years ago, there was a huge super volcanic eruption in Sumatra island. 74,000 years ago. That ash, I mean, you can find that ash in Siberia also. Here also, in Maharashtra, very plenty. In India, you find plenty of these ash beds. It's a white, very distinct ash bed. It can be used as a marker horizon for age also. So, what is so big deal about it? It seems, or it's kind of now established, hominins were evolving. Maybe Homo sapiens are already there. Below the 75,000 years ash bed, we find a lot of fossils. Or this, at least the evolution suddenly kind of stopped at that point of time. So people have theories, maybe there are evidence, I have not studied a lot, that a lot of animals, particularly human beings, died out during this period because they were blanketing for a very long period of time. There have been no vegetation, nothing, or maybe wildfires would have been there, and yes, no food, so people die. So it does affect. But if you go back in time, I'm talking about large-scale eruptions. Yes, like that, there have been much larger eruptions also. So yes, during that time, what kind of climatic effect we have, people model only. There is no direct evidence. I mean, proxies yet, other than knowing there is an ash bed. Is that something still developing?
So, can we use the isotopes that are there in those ashes?
In the ash, well, ash will tell you the source. If you do isotopes, you will tell where from it has come. You can find out its parent volcano maybe. But how it has affected climate, you have to go to records after the eruption. So yes, I mean I have not done work, but I'm pretty sure that you go and check, you'll find some work. People are maybe already doing it.
The co-evolution of like the East Asian monsoon and then so what are your comments on that after that?
I'm not a monsoon man, but yes, I mean they could. Yeah, we know that Asian monsoon, we call it what you call Indian monsoon, Asian monsoon, and East Asian monsoon. They probably came into existence same period of time. Here it is very clear that it is because of Tibetan plateau, let's say. But there, the records, interestingly, it's a completely different system. But they also say around same period of time, at least all the Chinese work what I have read, around same time it evolved, and probably Oligocene, right? So how that happened, I'm not that expert to tell you, because it's a completely different system.
I like what about your comment on tropical climate influence on polar?
On polar,
Yeah.
tropics affecting polar.
So thank you.
Sorry, it took so much time.
But it has taken more time. Nice
So,
one.
so
I will go.
Okay.
अच्छा तुम्हारे Gmail में भी
Okay. Okay. Good morning, everybody. I'm Ravi Bhushan from Physical Set Laboratories working in Geosciences Division. And I'm basically an oceanographer. And I've been working with, and of late, last few years, I've been working on paleoclimate, trying to venture out in paleoclimate.
what you are saying, something is.
Okay, I'm sorry. Okay, so I worked initially with universities, radionuclides for understanding the oceanographic process. For last two, 3 decades, I've been working on radiocarbon. Initially, I was working with conventional techniques of radiocarbon. I will explain what is conventional. That means counting decay methods. Only of late for last 7-8 years, I've been working with accelerated mass spectrometry. So, just the first talk, earlier talk, Professor Ray has beautifully summarized geochemical proxies. And that's very important because if at all you want to do paleoclimate, you need to know about the way geochemical proxies, how these geochemical proxies can be employed to understand various processes and various parameters that you like to derive. And I'm going to tell you that it's a very basic talk. So a take-home message will be what is radiocarbon dating. End of the day, if you are able to tell somebody what is radiocarbon dating, I'll be glad. So basically, I will tell you in a very simpler way how does radiocarbon dating works, and possibly a few applications you might be able to use it. So, as a radiocarbon dating technique goes up to the last 50,000 years only. This morning only Professor Ray was commenting that our total Earth evolution is 4.6 billion years, and radiocarbon covers only 50 kilo years only. That's true, very true, because there are other dating techniques which go through billion of years, like years, and many other isotopes like ketone, the stable isotope stratigraphy. If I'm going fast, please stop me because I have to do fast. Okay. So then, what happened in the last 50 kilo years happens to be the most dynamic, eventful. And most of the paleoclimate records are because these are old records. You don't find well-preserved records. So some of the most well-preserved records are in the last 50 years also. So there you can venture out for, and quite a large fraction of the paleoclimatic community are working on radiocarbon dating, like in the last quarter, in the last 50,000 years. And also it will give you very good absolute dating, absolute dates, chronology. So radiocarbon helps you when you're talking about paleoclimate to give you a chronology of the time. Because one is that when you want to talk of paleoclimate, or what time scales you're looking at, for the last 50 years, you can constrain with your radiocarbon dating technique. So basically, just to briefly tell you, my talk will go into like radiocarbon dating principle, atmospheric and radiocarbon, ocean radiocarbon variability, calibration curve, radiocarbon and biogeochemical traces. So I don't know how much I will be able to cover, but definitely I'll try to give you a basic feel of what is radiocarbon dating. So carbon, some of you know, three isotopes, 12 and 13, it is there present in the Earth. Okay, since the time form, Earth form, it is like there. So like carbon 12 is the most abundant, 98.9% carbon 13. So and carbon also forms the life form also, so that become more important. Although carbon is there everywhere, but it's only hardly 0.025% of the total abundance of all the metals. Okay, but the carbon 14 is not found in the Earth, and not in the Earth crust, or it is not as a basically formed. It is found in the atmosphere, and it's a very low abundance. Okay, it is something like 10 to 5 or 12%. Okay, so for one atom of carbon 14 will have 10 to power 10 atoms of carbon 12. So abundance is very low, so it is very difficult to do this thing. And it is produced by solar cosmic rays. So what happens is whenever the cosmic rays are coming, so they produce secondary neutrons. And these secondary neutrons interact with the particles like nitrogen and produce carbon 14. And basically, this is the reaction which produces carbon 14. So carbon 14, interestingly, the 12 and 13 are stable isotopes, and 14 is not stable. 14 is produced in the atmosphere only. Most of the production happens in the stratosphere, more than 10, 11 kilometers above. And then, of course, the production and CO2 production at the ground also, but it's a very order of magnitude low one. So carbon 14 is produced in the atmosphere. Since time immemorial, since the time Earth is there, since the time atmosphere is there, since the time cosmic rays are coming, carbon 14 is being produced. Okay, so that carbon 14, any natural system, which is like plant growth, our growth, anything which is happening, which takes up carbon in any form as a carbon dioxide or anything, the carbon 14 gets incorporated, and it gets well mixed in the system. And it is concentration is assumed to be remain constant, which I will complete like that. So basically, it is not stable and decays back to nitrogen 14. So because it is your radioactive, so radioactivity must have the school level itself. The most radioactivity, any radioactive elements has a certain half-life. So it has a half-life of 5730 years. That means if you 1 gram of carbon 14 you leave it, after 5730 years, it will be half of that, which will be left there. So this can be used for this half-life tells us how far we can go in time. So basically, we are with conventional techniques, we are able to go 35 to 40 kilo years, and with accelerated mass spectrometer, we can go to 50 kilo years, which I will tell you. Units of radioactivity is generally like geochemical measurements you will use ppm, grams per gram, or whatever is these units. But in your radioactivity, as you must have been taught, you cannot use it as ppm or these concentrations. You have to use Curie, Becquerel, or something because they keep decaying. Okay, there. So, as I told you, carbon 14 is formed in the environments, react with atmospheric CO2. Finally, because whatever moment carbon 14 is produced, the hot atom chemistry immediately gets converted to carbon dioxide. And that gets that gets incorporated in anything like a plant, human being, animals, anything which is system oceans, it gets incorporated in them. And from that time onwards, it starts decaying. So, and exchange in oceans and dissolved carbonate. So basically, from the time any system is created, it incorporates carbon-14, and from that time onwards, carbon-14 starts decaying. Of course, like in your dynamic system, as long as we live, suppose we are 50 years old or 25 years old, with the dynamic system, our cells gets replenished in a few years. So we will not get, even we do by carbon-14 dating, we will not get more than 7 years. So of course, we can't do with short-term carbon-14 dating. So carbon-14 dating tells you the time when that particular event happened. So of course, carbon-14, one of the basic assumptions in carbon-14, whenever we do any dating, we have to have the assumptions. Because we cannot, without assumptions, it's very difficult to go ahead. So we assume that carbon-14 production rate has remain constant. So like, so carbon-14 production rate is something like 2 atoms, approximately 2 atoms per centimeter square per second. So this is what it is. This is an atmospheric concentration is 13.56 ppm per gram of carbon. Because it has to be relevant to something. If you take 1 gram of carbon, you will see this much activity with 13.56 disintegrations per gram. That's what we will see. So these are assumed to be constant, but it's not the case basically. What happens is that because when they started doing carbon-14 measurements, I'll come back to how did they know that it was changing. But there are fluctuations because there are fluctuating cosmic radiations. You know that Earth's magnetic field, and that shields us from many things that you have in conducive climate and everything, all the radiation don't lead to a lot of. So this is basically how the magnetic field which shields you. And that magnetic field strength also changes with time. And that change in strength will lead to change in the carbon-14 production also. And change in solar activity, you know that sun goes through a lean period, active periods, and those will lead to solar cosmic rays coming, the change in cosmic fluxes, and that will also lead to your changes in your carbon-14 productions. And fluctuation in number of things on the planet due to sudden extinction of certain species, climate change, because what is that ocean, you know that ocean is a very dynamic system, 70% of the Earth is covered by oceans. Ocean takes up most of the carbon dioxide. And for many times, you know that like during glaciation periods, it's assumed that carbon dioxide was mostly taken up by the oceans. And during warmer periods, carbon dioxide pure. So it modulates the atmospheric carbon-14 concentration. That also modulates the carbon-14 concentration. Volcanic activity, because what happens in volcanic activity, whenever it happens, the CO2 which comes along with the volcanic activity is come from mantles. And mantles, which are millions of years old. And as I told you, carbon-14 has a half-life of 5730 years, basically. So there's no, when you're talking of millions of years, there's no carbon-14. Okay, when there's no carbon-14, basically it's called dead carbon. Okay, so that leads to dead carbon and dead potency. So then that leads to dilution of your atmospheric carbon-14 concentration. So if there is a volcanic activity, that also has that will change the atmospheric carbon-14. Consumption of fossil fuels. Fossil fuels, as you know that they're petroleum products. They're millions of years old. Whenever you burn petrol or anything, the last 200 years because of industrialization, we have been using a lot of petrol and everything. So that also has modulated the atmospheric carbon-14 concentration because you are introducing carbon-14, which is no carbon, your CO2 in atmosphere from the petrol, which are millions of years old, they don't have carbon-14, and they will lead to dilution of atmospheric carbon-14. That's why what happens is that less than 200 years, carbon-14 calibration, if you want to do, we will say not possible because there is Sue's effect, which is called Sue's effect is the dilution of the carbon-14, atmospheric carbon-14 because of the fossil fuel carbon dioxide. So fossil fuel, which is very old, has been burning for the last 200 years or more, and that has led to the dilution. So these are some of the things which have led to the change in atmospheric carbon-14. The last thing is nuclear testing. Way back in 1950s, early 1950s, 1960s. So most of the your nuclear tests were done in the atmosphere. So what happens is whenever you do nuclear test in stratosphere, artificially produce lot of radionuclides like carbon 14, strontium 19, uranium 236, plutonium 239, 40, so many other ideal system already have. So they get produced and they got distributed. And unfortunately, carbon 14 also was produced, and almost it doubled the concentration of natural carbon 14. So that's why carbon 14 was dating was totally obliterated beyond post 1950 because of the nuclear testing, because that introduced artificial carbon 14, which is resulting in an increase in that carbon 14 concentration. That's why carbon 14 we always use 1950 as the base year. I'll show you because I will be discussing about that. So 1950 was the base year which we used, because post 1950 nuclear tests were there, stratosphere, and most of the tests were done till the time early 96 to 9650 nuclear test ban treaty came, when they banned because they realized once you produce artificial nucleides and they get come to the back to us and come back to us only, it's very harmful. So there was a nuclear test ban treaty and they're not allowed. That's why you have most of the nuclear tests carried out underground nowadays. So that's one of the reasons. Okay, so nuclear test was another thing which post 1950 has totally changed the carbon. Till late, we still have bomb carbon 14 atmosphere, even though it has stopped maybe 50 years ago. Still, we have almost like 1 to 2% of carbon 14. So if you take any samples post 1950, because this is a concentration which is supposed to be reached a concentration, it has gone up post 1950. So now you take any samples post 1950, you give you future age. Okay, so that's why don't get confused. So that's why 1950 is the base year from where you will get it. Yeah. So I have already talked. I told you about. I'm sorry, I'm going this thing. The fossil fuels, which results in your this thing, because 18th century you have a lot of your fossil fuels were extremely exploited, and you have like a dead carbon introduction, which is called Soos effect. Okay, so people have now calculated, there are a lot of papers on that, which they said that like the carbon 14 concentrations has changed by something like 7 to 8 carbon per decade. And they make, suppose you want to make correction for carbon 14 in some of the samples which are post last 200 years, they try to make that correction for the fossil fuel or something like that. And nuclear test studies, of course, bomb radiocarbon was a bad thing, but but it was a like very regulated tests which are done, which are monitored, and still it is being monitored everywhere in the world oceans. So it has been used as a tracer, but it was used like an artificial tracer which has introduced as atmosphere. So it has been used as a tracer to understand studies. Because like I use bomb radiocarbon as a tracer to understand the AC exchange and many other things which I'll come to briefly. So just to tell you, this is the equation to whether carbon nitrogen cosmically produced flow neutrons your interact with nitrogen and produce carbon 14, and this carbon 14 decays by beta. Okay, decays by beta, producing an antineutrino and energy. This is the binding energy which is released as a part of the reaction. Okay, it was Libby, we got Nobel Prize. Okay, for he first did in 1946, and we are proud. I can tell you, Professor Lal, one of our mentors, used to be there. At that time, he was also working in carbon 14 on transmitters. He was at that time like why for that, carbon 14 production and all that. He was also working in USA. Unfortunately, it was Libby who made it. So, but we happened to from that group. Okay, the other year he was in TFI. He was our boss's boss, I would say. So he was very good with cosmic rays, all the finding papers are there by him only. And proud that that's why we have in our like legacy this cosmic rays applications. We can work on it in a much detailed way and an application we have been working for a long time. Okay, so earlier what happened is that I told you half-life of carbon 14 is 5730 years. Okay. But if they told you that Libby initially, because earlier it was 5, 6, 8 years. Because the technology improved. And with technology we could now finally after post 1980s or so, they know that it's 5730. this. Now it's very well known. I will not get into how they find the half-life. Half-life, they take a very pure carbon and then they try to per gram of this thing, they see the disintegration, physically they measure, and say you are missing atoms basically, and that's how they find out. So earlier they thought that it was 5,568 years. In 1980s, 70s, 80s, most of the publications were done 5,568. Carbon-14 has the maximum applications after life, initially to begin with. Because a lot of archaeological sites were there, they were dated using carbon-14. And it so happened that once in 1980s, they realized 1980s that 573 half-life, now there is a discrepancy. There are papers published already. So now what you have to do? So because part is that like somebody working on your suppose any site like Aryabhata, I will take our example, who had given date of something 4,000 years, and somebody uses 573 years, you get something 4,100 or 4,000 this thing 3,900 or something like that. So there's a discrepancy. He says no, that is age wrong. So now there's a becoming convention because in radiocarbon dating that whenever you report radiocarbon, please note because any of you are going to produce carbon 14 days, you will be given a date of so-called radiocarbon age. That is based on 5,568 years. And you have to report that. It is a convention for radiocarbon age for any publications that you have to give that so that if somebody wants to compare, earlier literature of Proxy 1950s, 60s, 70s, they should be able to read. And the calibrated age, then another thing is that radiocarbon age, which is called. This is based on 5,568 years. But another thing is calibrated age. Calibrated age is the one which takes care of all the carbon 14 variation in the past and the half-life difference also. Okay. So please note, so like whenever you doing radiocarbon dating, you have to report a radiocarbon date and and also the calibrated date. Radiocarbon date is mandatory, already it's 5,000, already 5,000, it is a convention which has to be followed. Okay, there are a lot of things which change your time, and radiocarbon in atmosphere, balance of its production, decay, and so many things are there. And why do they change your time? That you have to know. I don't be able to cover. So as plants, so basically now I'm telling you very nutshell how the radiocarbon dating works. So suppose whenever you are taking carbon, because we are quite a significant part of it are carbon. And as long as we live, then we live with the atmosphere. We take carbon 14 at some concentration of. Now, of course, we will bomb, but earlier when you are trying to do 30.5. So the day the human being or the plant or the animal life stop escape. And from that day onwards, this 13.56 dpm started decaying. Okay, this carbon 14. This started decaying. But carbon 12 and 13 are stable. They don't decay. There is other decay which is there like your biological decay. But if there is a biological decay means you just be converted to carbon dioxide gone. But that happens, then it happens for carbon 14 also. But I am talking of removal of preferential removal of carbon 14 from 12, 13, and 14. Only if you just keep it, it will remain as carbon 14 only will change. And that's the function of the half-life 5730. So whenever you do radiocarbon dating, basically you are trying to see the residual carbon 14. So the radiocarbon dating is basically residual amount of carbon 14 seen in the sample. So if you have something like 13.6, if you have 6.8, you know that it is one half-life is gone. And based on your typical equation of your you know that Nernst equation, decay equation, which is called e to the power minus lambda t. Okay, this is your initial 13.56. This is what you measure. Okay, and this gives you finally time. Okay, so once you measure that 13.56 is the initial. So if it has gone one half-life, you know that T is equal to lambda is a this is decay constant 0.693 by T half, which is basically again 5730. Okay. So basically on this is the basis of a radiocarbon dating. Whenever you are doing radiocarbon dating, basically what you are doing is trying to find the residual amount of carbon 14 in the sample. And once you know that how much residual amount, you can get the data. How do you measure carbon 14? That's a different thing. I'll tell you later. But keep in mind, this is how we go about it. So this is a very simple form of, I have told you we can read it, but I am not going through what is written. I'm just telling you that has it coming to my mind. And so all you need to know is that E0 basically, which is 13.56, which is known, we know. Okay, and small variations are there in the past. Atmospheric carbon 14 that can lead to almost 20%. So that also I will tell you how to be correct. And sources of variability, as I already told you, geomagnetic variations, geomagnetic field strength, solar activity, carbon cycle changes. These are led to changes in the carbon dioxide concentration, and so the carbon 14 concentration in the atmosphere. So you have to be knowing this to be able to do the calibration. And let me tell you, carbon 14 dating is an absolute method of dating. There are various methods of dating you must have heard about, but many of them are relative methods. Like you know, you need to indicate the method. Okay, lead to 10 decay technique. These are relative. Here you don't get age. You will see that with, suppose you see with time, with not time. Suppose with depth, suppose your profile and activity, you will get something. You will get a sedimentation rate or something like that. Let's do 10 million. But these are relative. From there, with the sedimentation rate, you try to find the age. But radiocarbon in one such is absolute method. It gives you time, exact time, what happened at 10,000, 15,000, 5,000, 2,000, something like that. So that's one thing in there. So this is one way you can do it. Of course, just to get it, because you need standards. Okay, standards are known. Okay, some known samples with known carbon 14 concentration. Because of course, what will be a reference? So they prepared like oxalic acid, which was made from 1890 wood. 1890 wood, what they did is they prepared the oxalic acid, and that's like supplied by the National Bureau of Standard and MES, and we get that, and that's used as a standard. And for the blanks, what we need is something that does not have carbon 14. So many a times we use marbles which are millions of years old. So you have to see that they are not contaminated or undergone any further reactions. And then anthracite, okay, carbon. So that also is being used as a pure blanks for our carbon 14 dating. The blanks are required to know that what is the minimum, like a zero concentration. If you have carbon 14, what is the kind of activity instrument is giving. Whatever you do, no instrument gives you zero value. It has some baseline noise. It will be coming both because of your electronics and because of the chemical procedure or the procedure you follow. So that leads to some basically background levels for blanks which are formed. And that we need to know, which you have to subtract from the sample value and then compare with the standard. So standard is basically oxalic acid. And here in delta 30C, see what happens is you have to make corrections also because there is a fractionation corrections. Okay, what happens? Yesterday I think so. Professor Shreyas must have taught you stable isotopes and must have given you some flavor of the fractionations. So what happens in fractionation, as I told you, is that suppose you are looking for carbon, because I am talking of carbon 14. So I will be telling you about carbon 13. How to correct for, because whenever you do nature, there is a fractionation. Because suppose you take carbonates, delta 30C of carbonates is 0 per mil. Okay, plants like it is minus 25 per mil. And grasses, if you look at it, it is minus 13 per mil. And if you are taking same samples, contemporary samples of same age, these three samples are there, and you are dating, you will have different ages carbon. Marginally different, but different. You will ask me why? Because they carbon, because the way the carbon is incorporated is being fractionated in that particular system. So yesterday you must have also told you about the mass dependent fractionation. Because fractionation is only mass dependent. There is non-mass dependent also. They are happy using very special environmental explains and other places. People are looking for non-mass dependent. But both in most of the natural processes, mass dependent fractionation which occurs. So whenever see carbon 12, carbon 13, carbon 14. So carbon 12 to is 1. Mass difference is 1. And carbon 12 to 14 is 2 mass difference. Okay. So if the fractionation delta 13C is 1 per mil, then fractionation in carbon 14 will be 2 per mil, double of what is there in carbon 12 to 13. And we always doing any measurements, we normalize with respect to carbon 12 only in carbon in your measurements of your radiocarbon. So you have to correct for this fractionation. Once you correct for this fractionation, and we normalize it to minus 25 per mil, that is the value of wood. At least initially, when they made standard with wood, so that's why they have kept minus 25 as a some reference value around with where you will normalize, not 0 per mil or 7 per mil or something, minus 25 per mil. So once you correct for that, all these samples, if they are carbon 14 dated, will give you same image. So that's why fractionation correction is also equally important, and that's how we do it. So you will have to measure carbon here. If you don't measure, still there are some like 10 years, 50, 30 years, 40 years, 50 years. Not very significant, but when you are talking at very high resolutions, these do matter. Okay. Please remember that you have to do. That's why. But many times people don't do because you're talking 10,000, 20,000, 50, 100 years will not make much difference. So you have, but like when high resolutions, you need to make this correction. So this is what I told you, and get to a calibrated ranges. As I told you, we started with the assumption that 13.56 of the CPM was the concentration count. That's not the case basically. That's changed in time. So how do I do it? How did they find out? Okay, okay. Then let me finish that. Okay, so this I have already told you. So just to get the thing, you can read it. But how did they find out? See, now I will just go back to the equation of n is equal to n0 to lambda t. There was something called initially people were working on 3 rings. I think she has told you 12 told about 3 rings. I think. So 3 rings form annual rings. Okay. So there are trees. So goes to something like thousands of years. You can physically count. The tree, suppose from 2023, you can go back 1,000 years, whatever it is, 1023 can go. In the equation, n is equal to n0 e to the power minus lambda t. Okay. T is known. Yeah. Suppose if I count 500, T is known. 1,000, T is known. I is known, na? Because you have physically counted, you know this is 500 years old, 1,000 years old. So you know that. You measure in that particular band, particular ring, the carbon 14 content. So this N0 should be 30.56. Am I right? This equation Sato said. So this should be, as per the decay law, this should follow. But when they measure, they always find some 5% difference, 10% difference, 2%, 10, 15%, and they will introduce. Why it is happening? Because if you do at some point, it is higher side, sometimes lower side. So that made them think that like carbon 14, whatever they are assuming of 13.56 is not constant. And that's where they came in calibration. So one good thing about radiocarbon dating is a very good calibration graph. It takes care of the past variations in carbon 14. Okay, so that's one good thing is that. Not only the absolute, it has a calibration also. So what they initially it came as a dendrochronological calibration. But dendrochronology, what happens? Something like 13 to 50,000 years so they could go. Because some of the trees in the redwood trees from the South America goes back to maximum 30%. What about the next 37 years, 1,000 years? So later they use corals and many other warp sediments from lakes and other things. Now they are access to 50,000 years. Now the calibration exists, and you can calibrate for any changes in the past carbon 14 concentrations, and you can get it corrected or which is your calibrated age. So that's why after the radiocarbon age, there is a calibrated age which comes in picture. Okay, so this is what it is. So whenever you are doing radiocarbon, this initial concentration should be known and need to be part of the biosphere. Fractionations, natural isotopic fractionations are there. And 0.95, if you are looking at it, why is the 9.95? because I told you 1890 wood. And I told you 1950 was baseline. Okay. So 1950 is our baseline. And 1890 for the wood. So you have to make the correction for till 1950. That's why 19.95 has come. So this is what it is. A1 is your standard, which is normalized, oxalic acid, which is normalized, SN is sample, which is normalized. And conventional radiocarbon age is minus 80, that can be put in this form. So people age of the samples, we can give up to 45, 50,000 years. And that is conventional when you talk that it's decay counting method, you can do up to, as I told you, 35, 40 kiloyears, and with the AMS, you can do 50 kiloyears. So, in fact, I have already told you this is the period. So, whenever you do dating, you will be having a problem of your calibrations. We are ages which are in last showing 200 to 250 years because you will say it's not under date your calibrated age. Okay, so actual half-life this thing, that's why we are needing. I have already gone ahead and talked to you because in 1950 it was observed that radiocarbon types were not matching the age of known artifacts from Egypt. Why radiocarbon date is not true calendar age? Because actual half-life was this way. So many of the earlier Egypt and all were dated with radiocarbon age of 5.6 and they found its discrepancy. Now it has been resolved with your new half-life. And they knew that, and that's why calibration came. And this is if you look at it, like last few years, the SUS effect, you can see that there is an increase in delta 14C. Plus, this is plus 20 per milliliter. Because if it is atmospheric, delta 14C is basically, this is what it is. As you know, delta 13C, same way delta 14C. Carbon 14 to 12 in the sample divided by carbon 14 to 12 in the standard minus 1 into 1000, just like in delta 14C. So this is how we represent. So when once you have standard value, suppose it is a 1950 sample. So standard is equal to sample. Then 1 minus 1, it will be 0.1. So sample should be here, pre-1950 should be here. But if going above that, that means there is some other contributions from some other field. Going below that means there is some dilution of carbon 14. So that one thing we have to do. And these are like D-rise effect, they are telling that 1700 and 1500 they have seen. This their activity to the sun's activity, solar activity, which they say that because of the so solar activity will change the carbon 14 production. That's what it has been done. And of course, these have been taken care of. So how did somebody construct this curve? You take a ring, measure carbon 14 in each rings, and that's how these curves have been done. Or now people use corals also, people use now your warm sediments also. Warm sediments, those of you don't know, they are in a very calm, cool environment in some lakes or even the some coastal regions, very marine regions. If there is not very change in the conditions of sedimentation, there very slow deposits with form layers just like series, and there you can physically count, and there is a warm deposits. Okay, so calibration, of course, I told you, this was dendrochronology to begin with. We started from clearings, we came to know that that earlier 13.56 was not the value which was there throughout. It has changed in time because of changes in the production of carbon 14, and that's why it was earlier called dendrochronological calibrations. But now it is changed to calibration. Earlier, for quite some time, like 10-15 years, initial days, you were only dendrochronological calibration. But now it's calibration, but there are so many other proxies that are used for calibration. There are different calibration curves for northern hemisphere, southern hemisphere, because the distribution, if you look at it, most of the continents are on the northern hemisphere, and southern hemisphere mostly is as ocean. Ocean plays a big role in regulating the atmospheric CO2. And let me tell you, CO2 coming from out from the oceans will be depleted in carbon 14. Right? Why? CO2 coming from the ocean will be in low carbon 14 compared to atmosphere. Why? Louder.
Organisms because of life.
What?
Organisms or organic.
No.
Carbon compensation.
Ocean has a big reservoir and it takes long time to circulate, thousands of years mixing. So whatever is coming, it will be 500,000 years older. Okay, so that contributes. That's why whenever they say glaciation time, that CO2 was was retained in the ocean, the carbon coating concentration, they were public carbon coating was higher. And deglaciation time, when the earth was warmer, then it was giving CO2 and the carbon coating concentration was lower. So people have seen correlations. And ice cores also, they do ice cores also trap CO2. They are measuring green light output and traffic ice core or whatever it is. So they do it. So marine archives, calibration, they are using coral reefs, they are using your this thing, sediments also. Reconstruction is done using seedings, as I told you, because now you know that year and you can attribute it how much correction required for every year. So very beautifully there is like those of you later, if you venture out into carbon 1418 or its applications, you will come across papers. There is a large number of group of people from all over the world who are involved in providing pages for the calibrations, and based on that 50,000 years calibration curves are being made. Of course, the calibration is a typical calibration curve. Actually, there was no change in carbon 14 concentration path. It should have been 1:1 line. But basically, this is the way the line looks like, because there has been change in carbon 14 concentrations. Okay. Sample collections. See, lot of people come. You should realize that a lot of people come to me. I have a store. I have this thing. I want to calculate carbon. First and foremost is the sample should have carbon. But most of the things in the earth has carbon in some other form, concentrations will have. So you have to realize that whether that particular sample form, it was in your direct the interaction with the atmosphere, and it was exchanging carbon from the carbon dioxide from the atmosphere. Then only can date it. You just can't date anything which are there under the earth and then it has come out and say carbon date carbon. So we need to realize that because carbon 14 is not present in the earth from the beginning, it is produced from the atmosphere. At that time, whatever is the surface of the earth was there, it got incorporated. Who exchanged? And from that time onwards, it has been. So that's why it's very important that carbon, many of you data samples, you should be careful that not all samples, every samples can be used as carbon. Those samples which have run exchange the atmosphere during a period when they live will be able to do carbon 14. It's very expensive because AMS takes nowadays people don't rely on conventional or conventional technique. We do have a PR both your conventional technique and also, but conventional techniques are little more time consuming. Also, it's expensive. Takes almost 2 to 3 days of processing and 2 to 3 days of counting per sample. And I cannot count multiple samples at a time. With EMS, I can count 25 to 50 samples a day. Doing a conventional technique, I used to do maximum 50 to 100 samples a year, which I do it in 2 to 3 days. That's a key thing. And I'll tell you, and also your amount of carbon. Conventional technique, I used to need a gram of carbon, and AMS technique, I need milligram of carbon. So you will say I have a lot of this thing, but if you look at it, because carbon basically, if you look at it, is not well preserved in any system. Decays are simple. The organic waste in your house, just throw in the car, nobody eats it. Decay will gone. So they are not preserved so well. So basically, preservation of carbon is very bad. So most of the natural samples what you find is in our earth has very little carbon. So conventional technique has a problem and you need to have so much gram of carbon, which is not possible. But with ALS, you might be able to get 1 milligram of carbon. So that's one thing that is to be there. Like more than one carbon source, because you have to see that the system what is being dated cannot have multiple carbon sources. It can lead to discrepancy. So that you have to ensure that your sample what you have taken has a singular source of atmospheric carbon 14 intake. You will be taking from groundwater or some other places, then you will have a discrepancy. And that discretion the person who's collecting the sample will have. And of course, you have to take care of that. You don't contaminate the samples while collecting, because anything you touch with your hand, you take a tissue paper, that's a carbon. Sometimes locally, paper में लपेट के samples देते हैं, they paper में डाल के तो carbon तो भर के आ गया. So you have to be very careful that when you collect the samples, the samples are kept in non-carbon related. Of course, polycanes are non-degradable, that's much safer. So you can sample collection and storage also is very important. Of course, these are some carbon content of samples because you should know a priori what samples you are giving and how much sample requirement is there for the dating. So then you know that you should know that like wood will have 50%, wood will have 50% collagen, and that means 7% only your carbon. So you have to accordingly provide sample to the persons who are going to be there. Okay, Libby method was there. It was simple old method where you just follow the decay. Okay. So earlier that which I did it for almost more than 2 decades I was working on that only. Last 1 decade I started working on EMS. So basically what you do is that the carbon 14 decays to nitrogen 14 beta and plus and Q. So you do it. So the counters are there, beta counters, eclipse scintillation counters. You monitor that and slowly because this is based on decay. So you as many the sample more than this thing. You used to get sometimes 1 gram, 2 gram, 3 gram or something. As much sample you get so that we get enough counts and we can reduce the time of counting from 3 days to 2 days or 2.5 days. So those used to be cumbersome, but it used to be one of the. But here it is like selectively doing. Suppose you want to do 4 amps. 4 amps, you take a sample, speaking 4 amps, 300 per added 1 milligram carbon, 10 milligram of 4 amps. 4 amps is calcium carbonate. It is 12% carbon. So 1 milligram carbon I get from 10 milligram. So 10 milligram I need 300 species of 4 amps. So somebody has to sit and method and that with that you can't do this conventional techniques. So bulk dating was possible with conventional technique, not possible to do 4 amp dating. So that's why OMS becomes very handy. So this is the conventional technique where you do that and simple equipment, just measure the beta decay counting with the earlier one. Long measurement times due to low activity, big samples, more than 1 gram. You might be thinking 1 gram diametrically therapeutic, but not always that is the case. Because sometimes when you are taking a profile, there are very little samples and that carbon content is less than 1%, 0.5%, 0.1%. And it becomes very difficult to get ample amount of carbon in that. Accelerator mass spectrometer. Okay, you can measure ratios. One good thing is that we don't wait for the decay. How many numbers of your carbon 14 atoms are there? We directly count it. Simple. You see, there's no time. Okay, we count the number of atoms of carbon 14 which is there in the sample, and we count the number of with respect to the carbon 12 or carbon 13. We can use either of them. These are very fixed. You know, carbon 14 how much is there? Proportionally, you know that or that. So it became a very revolution for carbon 14 dating because it allowed not only allowed very low amounts of carbon, but also we could do that. They could do that. 10 minutes. We could do like very fast. We could do something like 50 samples, 30 samples, 1 day counting. Preparation takes little time, but counting was very fast. Okay. This is a typical your typical AMS, how it looks like. In AMS, what happens is what we have is that you convert carbon 14 to this thing, negative ion. The secondary ionization we do. In that case, helium beam comes, the spikes. When your ionization can remove electrons or add electrons, we add electrons and we produce negative. This way. Okay, AMS. The ion source. We produce negative ion. And that is the one. What is the biggest interference for carbon 14? Anybody can tell? What is the biggest interference? I don't know why. Which will be the biggest interference of carbon 14?
Nitrogen.
Nitrogen 14. Kitna nitrogen? 70%. And nitrogen is 70%. And carbon 14 kitna? 10 to the power minus 12. Yeah, keep adding 0 nowhere. So few atoms of nitrogen is enough to keep my carbon 14 signature. So that's why we do secondary ionization, and in secondary ionization, one good thing is nitrogen does not produce. It produces negative ions, but it does not produce like simpler your secondary ionization. And that's where we remove most of the interference carbon-14. Okay, so that's what we do basically. It's ionization when we do here this thing ionization. Ionization detector. So there we ionize it, and we produce carbon-14 ions, negative ions, and then we pass through accelerator. So what happens is that in accelerator, I'm just briefly telling you how does an accelerator mass spectrometer works. So when you ionize, you will have carbon-14, 13CH, 12CH. Instrument does not know carbon-14 है, carbon है, nitrogen है. It knows mass. It is a mass spectrometer. It knows mass 14. तो उसके लिए ये तीनों बराबर है. So 14 mass it allows everybody. Whoever comes with the 14 mass it goes through. Now I have to remove all the culprits who are not contributing to my carbon-14. So what we do is that accelerator, that's where this accelerator comes in picture. What we do is we accelerate the particles at very high speeds, billions of electron volts, billions of volts. So like we have at 1 million volt, is a very big accelerator. This thing is 6.5 million volts, but you can do billions of volts. And what it does is, and then we have a stripper gas, which is argon. So what it does is, it breaks down the molecules. So when you break down, this will become 13C and H plus, 12C and H plus. So this breaks down. First thing happens is that all the interference which are 14 number mass, they are gone. And then it produces various ionizations, +1, +2, +3, so many. You remove electrons and various ionization states. So you can choose higher ionization state because what happens is all the interfering particles which are there still do whatever you like. No system is perfect. There will be still carbon-14, mass 14 particles which are not carbon-14. So still they are there. So what we'll do is that then we choose the charge state. To ionize to higher charge states, it becomes difficult for a compound or any other. So they will also get eliminated. If we do the higher charge state, so we do the higher charge state, we will not take class 1, we will take class 2. We will see most of them are 1. And that accelerator does. It strips up all the molecules, breaks down all the molecules, and also allows us to eliminate any other still remaining your carbon mass 14. And then finally we put it through that, and then it goes to the detector. Sorry, I came this thing. Cesium वहाँ पे था. ऐसे आया, high energy is required. Again, carbon-14. So carbon-12 and 13 also measure. Let me tell you, my AMS can measure delta 30. But it does not measure so much. Like in conventional mass spectrometer, like CS must have told you 0.1 punch. But here we do the one with font precise, but it's good enough for correction for fascinations. Okay. So this is how a typical AMS works. We at PRL do have a, this is the old generation. Old generation, your accelerator mass spectrometer was huge. I don't know if anybody has seen, anybody has been to IUAC or anybody had to IUP Bhubaneswar, they have big accelerators. The accelerator itself is more than this room is the accelerator tank itself. There are two this thing. And there are big huge rooms and all. And it's very difficult to manage, maintenance cost, manpower, so many other problems are there. Now they reduce it, they called it tabletop. This is not tabletop. It is in 12, sitting in 12 to PL sitting in 12 to 12 meter by 8 meter room. Okay, but it's still compressed. It's a 1 MB at PRL what we have. And in that, we are able to consider carbon-14. So here it's not only carbon-14, we can measure other cosmogenic building flags and we have 10 and 26 also. But it can be upgraded for your iron 129, calcium 41, 2006, protein 230 and 40. These are the future plans for our divisions which we are planning to do. So it can do. The accelerators at PRL is there. It has been working in nicely for the last 7 years. And as I told you, AMS 14 and does not produce stable anion. Negative anion produces. That's how we get this thing. Okay, low energy mass spectrometer selects only. And one big thing is that problem is that in the regular mass spectrometer, you will say that mass spectrometer is simple RMS mass spectrometer because it does not select mass by charge ratio of 14. Okay, so that ratio it does not select. And you can accelerate and you can remove all the molecular interferences. And of course, by your detector, you can remove that. Still, the lithium happens to be one of the interference like lithium 2 plus will be carbon 14 again. And that also interferes that we remove by mass relationship in the detector. Okay, so AMS has short measurements, less than 1 milligram sample, sensitivity of 10 power 15 minus 15. This is a highly complex and costly equipment. That is the one, but once you set it, but in country like India, we have one, but there are some other institutes, my main future will come up and should come up because we are going into Paleoclimate studies and there should be more access. Because I have gone through that 2 decades when I gone to the conventional, I used to really start for some few AMS numbers. So definitely we should have more facilities coming up. So Steiger and Pollard is one very classic paper that one which tells you about how to report carbon 14 data. I can pass it on to the unit I have that, and that you can use it. And half-life is half-life is this. Oxalic acid is one of the standards. And 1950 is the base year, please. And why? I'm told you already. And we are normalizing to minus 25 per meter because we have to normalize to some value because they use standard as good, which are the minus 25. They can look at it normalizing of minus 25. Okay, and uncalibrated means radiocarbon age or radiocarbon time is at carbon 14 years also. Sources of errors which lead to uncertainty consisting is variation in geomagnetic flux that has been changing, as I told you earlier. The geomagnetic field strength controls carbon 14 productions and changes. In 10 minutes, I'll tell you applications also. You took my 10 minutes, so I'll take. Okay, 10 minutes, I'll tell you applications also because we just sorry.
I said deep break is there.
Oh, sorry, I'll finish. Okay. Then modulation of cosmic wave classes, they will also add to that. And ocean reservoir, I told you how ocean regulates atmospheric carbon dioxide. And industrial revolution last few years, fossil fuels have led to carbon changes. And then now coming back to that, till 95 so far so good, but post 1950, everything very hot because of radiocarbon, bomb radiocarbon. Now post 1950, अब future में कभी 1000 साल बाद somebody dates it, तो उसको future में बहुत ही गलत एज मिलेगा, तो बोलेगा. But anyway, that's now in the past of this past. So but post 1950 because this year 1950 and supposedly nuclear testing has come. And if you look at it, this is what it is. The 1950. So these are like these are metric tons of TNT. These are some of the big tests which were done. Effective bomb yield, how much it was. On the right hand side is metric ton TNT. Left side tempo. It almost went to 1000 per mil. 1000 per mil means 100%, means double. And if you look at it, the blue line is the southern hemisphere core. Southern hemisphere, red is the northern hemisphere. Why is the difference? Continent to high Sarat test to not make. By the time it got mixed, it took. So that's why there's a lag there, and you don't see that particular peak there. And then finally, both of them, if you look at it, because atmospheric mix is much faster. And till date also, if you look at 2023, they are almost 1% or so. Bomb radiocarbon is still there. Still, we are not at the natural levels yet. Okay. Of course, it was a catastrophe. Bomb carbon 14 killed the bomb carbon 14 the natural levels of distributions, but it was used as a choice. I have also used very effectively to understand ESC exchange pattern for the CPS that how the ocean takes up carbon dioxide. If you look at it, almost 60% of the carbon dioxide produced is taken up by the oceans, and the ocean acts as a big purpose. Okay, and that's why we are in there, both in terms of climate and many other things. Ocean offers a lot of things. So that's why we are. So how ocean is taken, it could have been can be done this path. But carbon 14 path follows the pathway of carbon dioxide. So if you just measure the carbon bomb radiocarbon, so I use carbon 14. A lot of people have used. And like wine dating, old wine costs more. Okay, that all of you know. To take wine, you definitely know. And because they put in barrels and keep it for 20 years, 30 years. But usually that there are some lot of unreliable. So like way back in 25 years ago, I went to France. Okay, and there was a big lab in Gif near Paris, and in basement is one lab was there. So then I went there, sample depository was there. In the sample depository, there were a lot of wine bottles. I was very happy. I don't have to go anywhere. Yahi kaam karo, yahi sab kuch. Okay, I was very happy. So and I told her, very nice area you have kept wine also for people there. Well, not for drinking, it's for testing. Right? So that's when I realized that usage of that. So like that, I'll tell you from this. See, in this peak, suppose they say, suppose in 1995, they say for 50 or 40-year-old man. So it 1990, 40 only suppose 30-year-old. So 1965. Okay, hoga. But if you measure, somewhere it comes here. You carbon 14 content you measure because bomb has you can measure carbon 14 content. So then it knows that अरे ये तो 20 साल पुराना ही था. So a lot of companies before marketing.
So don't know where you can see the distribution. It could be 1985 or 1966.
Some cases it is dicey, but you have to see that. But like generally they do by 10-20 years का गड़बड़ करते हैं. So you can catch up in these things. Okay. So that way you can do it. So carbon wide dating will be. So bomb dating carbon is being effectively used for doing many other crop studies. It has got into so many forensics, biology, so many things. So radiocarbon has found a lot of applications for CMS. Okay, dating drug crops also. Even the like growth of various organs like kidney stone growth or so many other things and organs, how do they replenish? People have found using carbon tracer. Okay, YAMS I've already told you can detect samples. I'm repeating it basically as it looks like, and you can do large sample turnover. And this is like MS which is there. I told you, sciences division at here has established. I'm proud that it is working and it will be using. It will be available for I think so all everybody in India must be using. Okay, and this one is performance. I'm not getting into it, and we can measure. It has found large applications. Okay, because it's climate change. Whenever you want to do climate change, you need this thing. You need dates, Paleoclimate. You can archaeology. That's one of the biggest application all over the world. People have done glaciology. Also, people have done glaciology. I'm telling one of my students have worked. Okay, and hydrology, like groundwater movements and things. Very carbon dating. Geology, of course, it has a lot of application. Paleoclimate, planetary sciences also. Oceanography. There's so many fields. I could mention few only. There are forensic, land sciences, many others there where it can be used. Of course, we at PL can do 3 isotopes carbon 14, beryllium and aluminum. I will go wind up fast. These are precision of measurements. Okay. And of course, like ocean, any processes, a lot of people are trying to look at your surface acidification, denatrification, reservoir moisture, a lot of things. But if you have to give a chronological the last 50,000. Beyond that, there are other methods like Proxies, 100,000 years also. Like speedometers, earliest people were doing carbon 14 speedometers, but they found there's a problem. They use urine dating method, but we can do some places the carbon 14 method also. Exposure rate dating is not carbon 14, it is very late. Okay. One of the cosmogenic. One of my students is worked on it and done it thesis. What happens whenever the glaciers are there, and beryllium is also just like carbon 14 produced at small space. There is in situ production of the rocks also. So whenever the glaciers are there, as long as they are there, they are there. The moment they go back, they erode the surface and fall into the surface. And from that time onward, beryllium 10 production is there. You know the beryllium 10 production rate? Okay. Production rate, you know, so many atoms per centimeter square per second. And then you measure in the at 1 centimeter square how many atoms per centimeter are there. Centimeter per centimeter square there. This term again, divide one by other, you will get time. It's simple, I'm telling you very simplistically how do they call the weather glacier using beryllium 10. So we are one of my students has just done it and they like your value that. Change glaciers, how that's 20 meters from 80 kilometers back, how much time just take that, and movement rates and all that. Of course, CO2 atmospheric CO2 sequestration reverse, we will talk also like carbon dioxide sequestration because carbon dioxide increasing. How can we sequester this sky, remove carbon dioxide from the atmosphere? You can use carbon 14 as a tracer. Compound specific because when you are doing dating, in the oceans. Earlier they were organic carbon dating was done, but later they found that when they did some specific compounds, they found dates ranging from almost modern to 10,000 years. So you have to be very selective. Alkanes are all very refractory.
they can be secondary deposited. So you have to be careful when you're doing organic carbon dating sediments. So which fraction need to be dated sometimes. So then compound specific dating also became very good. During carbon atmospheric aerosols. Now very important because people are working atmospheric as sciences also. They try to find out that how atmosphere is getting contributed because of fossil fuels. There are two sources only. One is soil CO2, which is modern. Another is fossil fuel. So zero. एक का zero है. There are no carbon 14. एक का उसका carbon 14. There are two end members. You can find out what fraction is coming from. It's very simple. The people are working in many places. How much fossil fuel is contributing to atmospheric CO2? That can be done. CO2 uptake, I told you, I use bomb radiocarbon as a tracer. I can't go in details, and you can use bomb radiocarbon as a tracer to understand how the CO2 is being taken up or given by the oceans. Because finally, you want to know. The bomb radiocarbon inventory was known, as I told you, because it was when this is the time bomb radiocarbon tests were done, nuclear testing were done. It was well monitored. We knew the inventory of atmosphere. We measured in the ocean column how much bomb has gone. That is a way to separate bomb component. Then total this thing and how what is the exchange rate will lead to much of this thing. Based on that, we found out that 69 teragram of carbon is being given up by our agency, 49 in the ocean, and the bare Bengal survival was sink for this thing, minus means sink for CO2 because of your freshwater classes for so many years. Of course, you can do in porous. People are doing the carbon dating of pores. You can measure at different intervals of this thing. Using sediment core, carbonate, either in organics or perhaps to give you chronological core for doing any paleoclimatic studies. Statistic climate process readings also we try to do it. It is used in calibration also, and also to understand various climatic changes. Glacier erosion, I have already told you, and meteorites, of course, we are using very limited exposure. Lunar Lake and all people have done it, but it's not by Indians. It was given 37,600. I'm trying to get some samples from the limited possibly trying to give some. That's like some of the lone craters which are found in between. So when these craters are found, when that event happens, it can be done. These are some other applications. Stages of foraminifera, terrestrial lithometrites can be done using aluminum 26, the Delta exposure. Rock art, rock paintings, many of them 50. But many of the rock paintings are made by natural pigments, plant potted and flowers, food, and all that they use to do that. And they are organics. And you can just do it with DMS. Conventional technique में तो पूरा पेट निकालना पड़ेगा, तो रहेगा नहीं. But you can take in LMS, you can take one chip of it, and you can do that. And original carbonate associated with biomedical application, archaeology. This is what it is. Thank you very much. You can read it out.
So, question one or two. How do we discuss a team?
No problem.
You push, yeah, yours.
From?
My question is like, how long one should go when we are dating the ground? I mean, if we are getting wages, maybe around 40,000, 50,000, we really trust the data.
See, beyond 45, 50, it is like a little dicey. You are like playing it. Until unless the precision is good, you are able to decipher the, because there is five, there always in any system to noise to the your signal ratio. And if your signal is way above, many times when you say 50,000, many labs are not able to do that. You have to see that you have to how much confidence you put. That lab can tell you that no, this stage is can be dicey, and you have to just take it as a background noise. It could be because of little contamination here and there also can lead to your that kind of thing. So basically, 45,000 is safe bet, but people do to use 50,000.
If you are a little inside of the medical terrain, you want some so I'm currently learning about it.
Which one?
Beryllium 10 and 6.
Okay.
So my question is like, if we have multiple exposure of a certain sample or area like we are working, how can we date that?
See, you have to do that like rock only. You have to use separate pots, and then in that from that pot you have to extract beryllium. Okay, and in that you have to do it. But one thing you have to ensure, because when you are talking of glaciers whenever even their annual is receipts annually and there's progresses annually also, and long term scale also. You have to see that because it is the last time when the glacier was there, when it goes off, and you have to see a polished surface. Because what happens is, like it has happened like tens of thousands of years, there are a lot of natural vessels. So that particular surface has to be very well preserved. So of course, when we date it, we have dated so many maybe 100 dates, but real like bet we can put on 20 which are good polished surface. We know that they are doing that. We have to identify the proper sample. Basically, it's most important to take bedrock, because there's no one paper will be coming. You can see that that's where we are discussing whether to use moraines, bedrock, or the boulders. So bedrocks happen to the first time.
So thank you. Great. We can break for tea, maybe for 5 minutes. Thank you. Okay. ठंडा हो गया ना क्यों पिला रहे हो क्यों पिला रहे हो अच्छा तुम्हारा ईमेल में मैंने भेजा उसको थोड़ा सा ईमेल
That's why I think the cost approximately I'll show you the details. Hello. Welcome back. So now that we have Dr. Waliyur Rahman from NCPR Goa, and he works on ice cores, corals, and oceanography, and many more things. He has well-established lab, so he would share the what are the things you can do with the ice cores and corals to reconstruct the past sedimentation. pH. It's pH. So, so here, Dr. Waliyur Rahman.
Thank you, Navid. So it's now good afternoon to everybody. Actually, I did my PhD PRL, so most of the isotope geochemistry which I am using as a tool in a paleoceanography or paleoclimate, which I learned from PRL and Professor Jyoti Ranjan and Professor Ravi Bhushan, they actually taught me in the lab. So many of the things that probably I will be talking about the technique, method, particularly the isotope geochemistry, which I learned from PRL. And then, so there I never worked on paleoclimate or paleoceanography, but then the job I got at NCPR Goa, and then the challenges I took, and finally my learning method from PRL, finally I transferred to Goa and I'm using as a tool. So it's nothing. So similarly, it's actually, it's if you have a fundamental knowledge of the subject, of the methods or tools that you are using, no matter the subject is, you can anywhere, you can use them, maybe some oceanography, paleoclimate, earth surface processes, or glacier studies, or ice core, anywhere. So, okay, so with this note, I am going to start, and then, so I have my presentation of the in two parts. So basically the first part is a paleoclimate based on Antarctic ice core records. And then second part is the paleoceanography, paleoclimate based on the coral records. So, yeah. So, paleoclimate, if you see in India, many parts of university institute, you can see that people are working based on tree, based on lake sediments, based on many other records. But this is unique in a sense that ice core records is not available everywhere, or so it's an opportunity for me actually to take up, and then I got opportunity to work on the ice core, because that is the only lab in India so far that we have a ice core preserved in our record. Means we have taken the ice core from the Antarctica, and then we have reconstructed the past climate Antarctica, and then it's some relation with surrounding oceans or continent. So, okay, coming to the ice core now. So ice core look like this. So if you see, so basically the project that NCPR I'm working on, that is the cryosphere and climate under which this ice core research actually belongs to. And then the why it's erratic? This.
No, this is through. That is your mouse actually.
Okay.
It's not a pointer. It's
Okay.
mouse.
Okay.
It's moving here.
Okay. So, so mission is understand the past climate and to know the future. And then oceanography that I'm using, trace element and isotope studies, mostly in the ocean and southern ocean. And then my mission actually diagnosing the ocean health and then exploring the ocean well. So, okay, ice core. So, ice core, many records that you can reconstruct. There are many, so I have listed some of them. For example, temperature, relative humidity, moisture transport, dust transport or dust source in Antarctica. So Antarctica is like this. So if you see here, Antarctica is almost 4 times size of India. So now you can imagine the continent, and it's covered by snow. ice. So it's a huge, and then this is quite pristine environment in Antarctica. So you will get all these records if you take ice core from this. So atmosphere composition, I will come into that individually, how actually we do. And then atmospheric composition, basically the how CO2 concentration was thousands of years ago. You can reliable record only from the ice cores. Then volcanic activity, many of the volcanic activity that have been recorded in the ice core records. Then solar activity. So these are the records. There are many. So these are the key actually meteorological parameter, climate parameters that we can reconstruct based on the ice core records. And then now question is why so special about the ice core? So one thing is that ice core gives very high resolution record. It's compared to instrumental records. So if a monthly resolution you can reconstruct. I will come to that ice core how we do. And then it can go beyond several thousand years. So far, the most of records that almost 800,000 years. So you can imagine. And some of the records not that systematic, but even the blue ice region, some 1.5 million years. That paper came last year in Nature. So Cambridge group they published because CO2 record was not beyond 800,000 years. So most of that gives 800,000 years. But beyond that, so there was some attempt made, but again that was not based on the ice core. So it says some blue ice region, but there is some old ice. So they have measured the gas CO2 in those, and those are up to 1.5 million year records, but not systematic record like ice core.
How did they date those?
Those are dated based on helium or something like that. So it's an absolute method. So in the gas, they have measured some gases, probably some helium, something like that. So
CO2 also. They start CO2.
No. CO2 is the record.
So probably it's a helium, probably helium, and then uranium decay to helium.
Beryllium?
No, not beryllium. So beryllium will not get enough beryllium in those because so will not get. Okay, so and then this Antarctica is relatively pristine. You do not have any unstable, and then so it gives better time constant. So if you have any climate record that you are planning to reconstruct, then you should have a well constant chronology. If you do not have good chronology, actually it does not mean much. So you have to have a good chronology. Then large of the parameters like I have listed here that you can reconstruct based on the ice core, which is not possible in many of the natural archives. So that is why it is very special. So, but then again, I'm telling it's a very expensive and logistically it's very challenging. So you have to go to Antarctica. So before I start actually coming to Antarctica, ice core I'm giving as a whole, but then it's a, since I'm involved in Antarctica, there are people also working not from our group, but involved in the polar regions like Greenland. So Greenland also same ice core you can here. Himalaya so far from Indian side we could not do because Himalaya there is some problem logistically. It's very difficult. Terrain is not that supportive, and also there are some other challenges. So though it's near to us, but Himalaya so far we have not. The drilling somebody was asking that why not from Himalaya. There are some attempt made, and it said the one good record Gulia ice core that is from the other side, Tibetan side, and you have a very long record from the Gulia, but not from the Himalaya. Okay, so coming to the coring, that how we drill actually. So we go to Antarctica. I have never been in Antarctica for this purpose or other purpose. So, but in our team, people have gone to Antarctica, and they do in a, let's say they have a convoy because container with several equipments, manpower, generator, fuel, everything they have to carry, food, every stuff. So logistically, it's quite challenging. And then the drilling site. So before setting up drilling site, you have to have a geophysical survey where the coring you will get a good stable record. So finally, so this kind of activity before the drilling. So you have to go there, and then you have to go to that particular site, and then finally, but but then it's not from actually Himalaya. Actually, I have gone to Alaska, and so long ago, almost 5 years ago. So these equipments we purchased, and then as a part of the training, so I went to the Alaska, and so it's a northern side. It's a
Yes, I want curious to know how long core from Antarctica or Indian side has been.
It is so far we have drilled up to the last one, but so far we have not reconstructed. It's a 500 years. We can length is almost 65 meter. It is 2005, but after that we had a last expedition. We went up to 500 years. So now 100 meter one we have, and then more than 100 we another one, the latest one. But then some planning is now going on with vast British Antarctic Survey in Norway to have a Holocene record. So deep drilling. Yes. So we have a plan now. Actually supposed to happen this year, but because many of the issues came and then it did not happen. But this year we had a plan to go for the deep drilling, at least for the Holocene. Yes. Okay, so this is from not Antarctica, this is from Himalaya. Because yeah, so Alaska, I went for the training purpose, and from there they show the how to drill, and then the demo how machine works, so like that. So that just to show the how it look like the ice core is. Okay, so and then so Antarctica got the cold condition. Then after drilling, we brought to Goa 30 degree, 35 degree, all the way from the Antarctica. So it's a 1 month of journey by ship, and then but we maintain the condition minus 20 degrees. So it's a referred container. So drilling and then the transportation all the way you have to maintain, because it's a minus 20 degree. So even in the lab where we preserve, it's a minus 20 degrees. So if you go to our institute, we see that we have a lab, ice core lab, where all the time it's a minus 20 degree, and then people are maintaining lab. It's quite expensive. Yeah, and then there are room where we process the sample. I will show you that. So which is minus 15 degree. Okay, so this is how, and then what we do basically, this is a ice core, and then we cut it in 2 parts. So one part is the archival half, so we don't touch it. Straight away goes to the archive, and then another part is the working half. So that part we work for measurement of several parameters. So what we do, so and then gases so far we have not measured, but you don't have to, because if you have to go to already these things are done. So we mainly measure anions, cations, and then stable isotope. That is the routine we do. So yeah, so these are the parameters that we measure. Okay, these are all IC, chromatograph, IC, trace element for measurement, and stable isotope. So these are routine measurement that we do, and it's thousands of samples, because ice core we have to do very high resolution to for many purposes. One is for the chronology. So in a year, typically 1 year, let's say 10 samples, 10 to 15 samples. So if you have 100 years of year, then it is almost 1,000 samples multiplied by 10. So we have to measure thousands of samples and all the parameters. So all the anions, cations, stable isotopes, so it's a lot of measurements that we have to do. Now, okay, and then any reconstruction you do, first thing that you have to do the dating. So and then dating, you have to have a very good chronology. And then what you do, so there are several steps that we follow for the dating. First is the ice layer identification. So there are many actually methods, but then which other steps that you have to follow. So ice layers identification based on many things. So based on some, let's say there are some scanner, you can scan it and you can see, but that is very crude. But it gives some kind of a handle that okay, the layer how look like, and then you measure the stable isotope, measure ions. So sodium, potassium, calcium, anions, chloride, sulfate, all these things. And then radioisotopes, I will tell you why already Professor Bhushan has already explained that radioisotopes, tritium, that actually produced once upon a time means during the bomb testing. So during the time it was 1960 to 1962 or 3, something like that. So that time maximum actually bomb testing happened, and then we saw that tritium peak in those ice core records. Then summer, because it's an atmosphere homogeneous everywhere you will get an ice core we have seen. So we measure. So that give one of the type points. So if you are doing chronology, so that tritium give the one of the types. So there are many. I am coming one by one. Then the volcanic peak. So we measure sulfate, and then sulfate. If you measure the sulfate, then there are also non-sea salt sulfate, and then volcanic. So you have to calculate that how much is actually non-sea salt, and then you can get the volcanic, the sulfate peak. And then you know the corresponding what time the eruption, its historical records are there, and then you can match that, and then you can. So these are also giving one of the type points. So 1, 2, 3. So if you have a so I'll show you in my next slides. Okay. So these are there are now many compilations have come for the volcanic records in this. So there are many actually. These are historical. But there are also thousands of years like Toba eruption. So which is so depending on your requirement, you have to choose the record of the list of the records. So this is our time scale. We know that we are handling what time scale our records. So it is a let's say a few tens to few hundred years. So then accordingly we have the records. So if you measure the non-sea sulfate, then you know that okay nearby, but there are steps. I'm coming how the steps are. So, okay, this is our record. The core is, let's say, 100 meter. So, we measure oxygen isotope, and oxygen isotope, when you measure, there is a seasonal variation. So, summer and winter. In summer, you will get higher value, winter, you will get a lower value like that. So, you can see. But problem is, it's not that straightforward. Nature is very complicated. It's not. So, some year, you will see that the signal is not clear. You don't see winter clear or summer clear. So then there is a problem. So then stable isotope, first order handles, it's works fine. So you will get, but during the counting, you can also make mistakes. So human eye, you can make mistakes, or maybe sometimes it happens that you are not able to identify the particular signal. So that can. So but this works. Similarly, you have also other parameters like chloride, sodium. These are all the cations because these are coming from the ocean during the let's say sea ice formation. So there is a sea spray. So winter has some amount of sea ice spray. Let's say winter is maximum sea ice formation, so it gives maximum spray of sea salt sodium. So accordingly, those signals will be preserved in the ice core record. So if you have a let's say annual winter, you should expect more sodium. So accordingly, so all these parameters will measure, and all these parameters that gives handles to count or to resolve the annual signal, summer, winter, and then we count. We know the surface. Then when the coring was done, and then one by one you can go back in time, and then. But in the process, you will see that if you count based on the stable isotope, it is not the. I'm telling it's not so easy. It's very difficult. So based on one parameter you count, you will get one chronology. Then you come to the chloride, you will get another chronology, then another. So sometimes, let's say 1950 is matching with the other chronology in 1955, like that. So some way you made a mistake, or the in nature signals are not preserved, or something happens. Some other, let's say even in the after the snow deposition, there is also secondary processes. There is a wind erosion, so you do not know. So all these complications that add to the alteration of the signal. So you have to be very careful, and those are very tricky things. But if you have multiple parameters measured, and then there are some techniques, then you can optimize to have a very good chronology. Okay. So and then you can see here sea salt sodium, sea salt sulfate that I said that. So let's say Pinatoba, we know 1901. So these are all Tambora, 1815. So first order chronology that we get based on the oxygen isotope, then chloride, then sea salt sodium. After doing all these things, then we see that tentatively where it is going. Then accordingly, okay, 1981 here this depth represents, so this particular peak represents 91, like that. So these all giving us type wise. So let's say some handle that okay, up to this depth there are these type points, up to this depth these are type points. So we are getting, so these are actually helping us to giving that type points, so that is improving accuracy of our chronology. And tritium, one of the type points. So after doing everything, then you should get that bomb produced tritium at 1963, that the major one happened that we get the tritium. So somewhere when the 1963 you will get a 62. So here, so it is supposed to be, so within a 1 year of uncertainty it's okay, because there are also some lead lags, so 5 to 6 months lead lag, so you have to consider that. Okay, so within this, so after getting all these things, we then what we do, there are some method, static counter. So okay, I feel something is there.
Yeah, that's it.
Okay, so now I score, you are measuring many parameters. So let's say delta 80, then so you have something, and then sodium something, and then chloride, let's say chloride, you will get some chloride. So then sodium, then chloride, then also non-sea salt, sulfate. So that give some episodic eruptions of peaks, let's say like that. And then you have a tritium, let's say, so tritium, you can measure tritium. So it somewhere it will give 1963 one peak within this time, 1962. Then after getting all these things, then manually you cannot actually optimize. So you have to have some kind of algorithm to actually to optimize that, and then finally get the chronology. So there are some MATLAB has some codes, algorithm are there, and then that actually you can run. I have those all the codes and then some papers and manuals are there. And then if any of you are interested, and for other purpose you can also use, not only iScore. Similar problem if somewhere else, if you see, you can also this static counter, this freely available software package based on the MATLAB. The codes are written in the MATLAB.
If you are getting the annual layers, then
yes. So this is this kind of so first there is a new iScore from Greenland. It was tested and paper that published. So separately they have also published the method, and then subsequently there are many papers on the algorithm. They have published, and then they have given the freely available software package. You can use that, and if somebody wants any help to run those codes, I will help you. Okay, so these are on zip file you can see, and then these are the codes. So it's not very difficult. You can you have to install it, and then static counter, and then these are the folder. So you fix the path where you have to, and then you can give all the parameters. So you have to give the type points, manual counts that you have to give, and then you have to give the type points and then individual time series. Then finally it will give the optimized chronology. So I'm not getting into that algorithm. And then finally, so if you do the manually, so we got manually like this, but after running this, taking care of all the parameters, finally we get this chronology SD. Okay, so so the part which I just explained, that was related to chronology. Now coming to the science, basically of our interest, to reconstruct the climate parameters. So the first one, which is everybody is interested, that is the temperature. How the Antarctic temperature evolved with, let's say, last 100 years or 500 years. So already probably in the previous speaker probably explained that how actually stable isotope carry information from ocean to continent when moisture. So basically in the ocean, if you see, and then moisture, and finally when it's transport and then deposit as a snow. So it carries information, and then but the complication happens if you go, there will be successive events of precipitation, then there will be fractionation, and then finally rain, and then it will also get the signature of the temperature, at what temperature it actually precipitated. So, but then the delta H, if you measure on the snow, it's a multiple of many parameters, and then it is very difficult to based on delta H, to reconstruct, to know the temperature. So how do you do that? Then if you, let's say, in a given area, let's say in Antarctica or let's say in Greenland, if you measure the snow and you know the temperature, because modern day we know after 79 everything we know everywhere, because satellite started measuring everything. And after that also satellite together with the, let's say there will be a problem of the resolution, but recent time even satellite data together with the model data, then there is a reanalysis product. So 79, let's say ERA 5 reanalysis, that would very high resolution, very good temperature record. So 79, since 79, you know everything, and temperature, you know. Even if you have a, let's say, a nearby station, you can also, Antarctica, there are many, the station, they also last 10, 20, depending on the where the station was established. So one of the station that nearby, let's say, Novo station by Russians. So they have the record of last almost 50 years record of temperature. So like that, so if you have a different places, let's say delta T no measured and then temperature, then you will get this kind of a relationship. It makes that has a temperature signal in that. So you can based on, so in your area, if you take a core and then from this relationship, you can let's say from this slope of the regression, you can go beyond let's say 100 years or 50 years or depending on your core. So that way you can also reconstruct. There are also another way. I'm coming to that. So okay, so one of the record that we reconstructed in from Antarctica, that was last 100 years, so that shows increasing trend. That's based on this special correlation. So snow composition known and temperature known from that particular place, and then we got the relation. We employed that relation of co-regression in this. So we know, let's say we have a regression of, let's say, for some area, and then you can employ that regression. I'm going to come to the next one. So next one, what we do, let's say, another way you can also do that. So let's say you have an Antarctica, you have a nearby many cores. So as I said, the delta T is function of many things. It's function of temperature, let's say, or the distance from the coast, let's say relative humidity, source composition, how many times you went through the successive precipitation. So there are many. So it's really difficult. So but then that is also happening for all the nearby. If you have many records, so it is for the all the records. But then if you have a time series, it's basically a record from given area, let's say here Antarctica, and then let's say I have a core here, but if you have a many core nearby location, then you have a time series of different length. Basically, different length time series means basically the records. So then what you do, you get a common time series, common time interval. Let's say here I am taking, let's say, common time interval of this month. So let's say you have a variable time series, variable records of different length. So some are, let's say, 2013 to, let's say, last 100, maybe up to 1900. Another record is, let's say, 1980 to, let's say, 1950. So then you have to see the maximum records, and then okay, then you can get, let's say, reasonable number of time series record. So here, let's say this is a common. You are getting, let's say, 5 or 6 records from a given area. Then what you can do the, basically you can extract the signal based on the principal component analysis. You can do that, and then you can see if you are lucky. I'm not telling every time happen. If you are lucky, sometimes, and the principal component, first principal component, you will get very tight relation with the space temperature over this special region. So you can have a special region, let's say average temperature, and then PC on record, you can compare with the temperature. So for a given location now, we have a record 1979 to recent. Means after 79 we have a very good record. So any part of the Antarctica you can let's say you want to also know what is the record from this particular latest after 79, which is very good because satellites started measuring after 79 everywhere everything. So then you can the PC1 derived from the principal component analysis of the multiple ice core records, and that PC1 you can correlate with the temperature from that particular region, average temperature. So this PC1 you will get the temperature, and if you are lucky you will get it. But if your records are good, chronology are good, but problem happens that the synchronization sometimes also many of the cores are not let's say there is a uncertainty 2 years or 1 year, so one particular time peaks are matching with the other one. So if are not well synchronized, then correlation sometimes that has a dramatic effect. So you will not get correlation, that can kill your correlation. So many of the times it works because Antarctica things are very systematic. So you don't expect that much. So still we get correlation in one of the records. So here DML Browning modular region, we have a records of last 100 years, 200 years, and then we got the PC1 which is tightly correlated with the ERA 5. ERA 5 is the recent one, the reanalysis temperature, which is basically model as well as the instrumental record. So that is ERA 5 is very good product for the temperature. So you can do that. And now you have a, let's say after 79, let's say up to 2000 year, that many numbers you have a data point, and then you have a regression equation. That regression equation you can employ for the entire record. So if you see the first one, I actually correlated this one, and then I have gone beyond the 79, but there is underlying assumptions. The assumption is, any idea what is the assumption? Assumption is if the relation itself is changing, stationary, no, it's not stationary, then this reconstruction may totally wrong. So the underlying assumption is that, let's say with a reasonable duration, last 20 or 30 years, we have a correlation which is a stationary, and then you are employing that regression equation beyond 79. So that assumption you have to, before telling the reconstruction, you have to also say what are the underlying assumption, and the key assumption is the correlation was stationary, at least within this time window, means our interval that we have reconstructed. Okay, so then the trend is okay. I'm not getting into. So then another stuff that we do that is the moisture transport history, relative humidity, all these things. So stable isotope already some preliminary already given. So basically, if you have a meteoric line, somebody already given this stress has given. So I'm not getting into much. So meteoric line, so that has a relation with that. So it's a global meteoric line, and any deviation that is basically it's a kinetic fractionation, and then you can measure it. So we call it d-axis, and that is a function of relative humidity. So basically, a change in the evaporation rate, so that effect on that d-axis. So you can actually use this particular parameter to know that the moisture source or transport history. So then indirectly you can also many things. One of the things that I did for one of the papers that I published, so that I have reconstructed the sea ice expansion. So Antarctica is surrounded by sea ice, and sea ice is one of the critical components in our Earth climate system. So Antarctica, entire continent, even this sea ice also in the Arctic. Entire Arctic is all covered by the sea ice. Similarly, Antarctica is surrounded by the sea ice, and then sea ice, there is a fluctuation, annual fluctuation, seasonal fluctuation, and with time also it's changing. In a long-term change also you can see. So I wanted to see that how the long-term changes in the sea ice based on the d-axis parameters. So what I did actually, so if you see the annual, even in the annual record, because satellite record, if you see, So summer you can see sea ice shrink, and then it is like this. So you have a more open ocean surrounding Antarctica. And then winter that expanded, and you can see several thousand kilometers expanded, and then open the ocean is covered. So there is a large fluctuation in opening and closing of the area available for the moisture. So moisture, all the moistures coming from the nearby or even for the long range transport.
You want me to ask? How do you distinguish between sea ice and glacial ice, which is entering into the sea?
Glacial ice. Glacial ice mostly
Sea
here.
ice will be frozen
No.
seawater.
Yes.
Glaciers are also falling. They are actually land ice.
But that does not actually. Sea ice is it's a very you can distinguish that ice is from the continent, and the cell break and then it transports. So those it's a very massive sea ice. It's a huge thickness, but this sea ice is few meter. Let's say 1 meter, 2 meter. It's not very thick, and then pattern is different pattern. So visually, by satellite, you can see the sea ice, and this sea ice is everywhere, and those are the ice that you are basically broken ice sheet or that iceberg. So that is it's a part block, and then it breaks somewhere where there is a glacial flow, breaks, and then it transports.
I have
that is a even bigger than our ship. So that sea ice is very different. This is a sea ice. It's a newly formed every year, seasonally formed. It's a very few centimeter to few meter.
So you are telling albedo ratio will decide that.
Albedo is a phenomenon which the light reflected back. So other it's a sea ice and a
The satellite algorithm will consider the albedo ratio sea ice to the difference between these two.
Definitely you can. Based on the satellite, you can. But albedo is different. This is based on some spectral these things. So albedo is a sunlight which is reflected back. So that is albedo. So depending on the the house. Okay. So you can. So now the challenge. Okay. So now coming to this, I think so there is an annual seasonal fluctuation. So summer there is a shrinking of the sea ice, winter there is expansion. So then availability of the moisture varies depending on the availability of the open ocean surface. So now you can see that then I also took the another supporting parameter, that is the sea salt sodium. That is also continuously there is a spray from the open ocean. So when there is a sea ice formation, there is a sea spray. And then the sea spray basically sea salt and sea salt sodium. So if you have a more sea ice formation, then you can see there is a more sea salt spray in the ice flow, means in ice sheet. So then it is very well matching with. So we know that this thing. So d-axis wherever we are getting very higher value, so that indicates there is a increase in the distance from where moisture is coming. So basically expansion of the sea ice, and then vice versa, and which is supporting with the sea salt sodium. So that was the thing that we based on the d-axis. So d-axis is for some other purpose, but I could use d-axis and use it very much, and that paper I told you. Yes. Okay. Okay. Then another thing that I'm coming to the solar activity. Not only solar activity. So basically, based on the production. So beryllium 10 production is very tricky, but there are other, let's say, nitrate. Nitrate also undergo photochemical reaction. That also but the nitrate. So those parameters you can also solar activity. So if you say solar signal, how it will be, but then problem is there are supernova explosion, then that has a cosmic wave flux changes, and there is a earth magnetic field. But then if you see the time scale, though this is a event, but it works in a longer time scale. Earth magnetic field varies in a longer time scale. Whereas solar activity is the solar cycle 11 year, 12 year or sunspot activity that we see, that is a much shorter time scale, 11, 12 year time scale, 11 year time scale. So those things we can, we can reconstruct. Okay, so basically beryllium 10 beryllium 10 has a 2 beryllium 10. Already told. So it's a meteorite. There are 2 beryllium 10. One is the meteorite, another is the produced within the rock. So so this ice core beryllium is actually it's an in situ, meteorite. So there is a continuous production of the meteoric beryllium, and there is a fallout. And that production actually, how much it will be, that depend on the solar activity. So then you can actually reconstruct based on the beryllium 10 measurement, but the amount of beryllium is very small, so it's not that easy because you have to have a sufficient number of. There are some reconstruction done, but it is not. People are not comfortable with. Means not everywhere. You have a very good AMS, high capacity AMS, and then because here you have a few atoms. The overall 10 to the 6 atoms per gram.
This scale.
This is a 10 to the 6 atoms per gram of snow. So 1 gram.
Number of atoms.
Atoms, yes.
But 10 to the power 6 number
atoms
of water molecules.
Yes. So you have, let's say, to measure a quantity, let's say a measurable amount, we have to have a good amount of snow, and ice core sample we have also limitation because you have to measure multiple parameters. So for a given day, let's say 5 centimeter, you have how much? So then what some people are doing, they integrate the samples, gets a kilo, 1 kg or 2 kg of ice, and then again you are actually spoiling also your samples. So it's a very tricky, it's not that easy. So 10 to the 6 atoms, you imagine. Now coming to the gas. So you can, based on the ice core records, you can reconstruct the past atmosphere composition. Okay.
There is a second part also.
Second part. Okay, so I will quickly go. So CO2, okay, now I'm going. CO2, as I said that Antarctica ice core record that provide 800,000 years of atmosphere composition record. Let's say the CO2, most reliable CO2 record comes from this ice core record. Now, okay, so this part is done. Can I quickly move to the coral? Coral, okay? Okay, I'll take questions at the end. Okay, Coral basically it's also gives very high resolution record comparable to instrument records like ice core because it gives seasonal to annual signal, and then you can reconstruct SST, surface salinity, pH, nutrients in the ocean. So the attempt that I made, the reason that I want to do, you know that one of the greater challenges now we're going to face, that is the ocean acidification, because rise of the atmospheric CO2, then this CO2 and the seawater carbonic acid, and then carbonic acid again dissociate hydrogen ion and then bicarbonate. So if you have more CO2, you are producing more hydrogen ion, which is basically you are decreasing the pH. pH is minus log of hydrogen ion concentration. So then ocean is becoming acidic. Acidic, many people actually misunderstand. So acidic, it doesn't mean that seawater is acid. So still is basic, but the change in the, it's a log scale 8.1 to 8.1 is change in almost 30% of the hydrogen ion concentration. So it's a log scale, and that is quite significant. So because of this acidity, now you see that calcium carbonate cells are started dissolving many of the global ocean, and then you see that ice core CO2 record, and then we can see pH how it is evolving. So like that. So and then there is a model prediction that pH, how pH is going to be with a given CO2. So okay, now okay, just to give a flavor that how pH scale is, that different products. So if you say lemon here 2 pH, then bleach how it is. So just to give a flavor, many people do not know, then you can have some idea. Okay, so now future ocean, no, I'm not going to do that. So what my focus is now here actually to reconstruct the past ocean pH. So coral records, so coral, first thing that I said that we have to have very good chronology. So first, what you have to do, we have to cut the coral along the growth axis. Then you have to do the X-ray, and the X-ray you can visually you can identify the layer. Sometimes also there is a tricks because missing layer or double layer like that. So there are some complication, but still you can do that. So and then okay, so if you have so test element ratio that we measure to actually do the chronology or to know the SST. So here we have a very short record. Already we know based on the many Hadley SST or satellite record. But if we have to go beyond 79, then again this method that you have to measure test element ratio, then you can reconstruct the past SST. So you know that the basic principle of this test element using as a SST proxy, basically this ratio depends on the temperature, because the how much it will be the ratio, it's again depend on the KD1, the distribution coefficient, and that is also depend on the temperature. If you change the temperature, the ratio is going to be changed. So then based on the principle you can, so any change, so first you can calibrate. So in my here you can see the strong shape by calcium SST, because this SST already we got because our length is not that old, so we have already record and it's pretty tightly correlated, not that bad. R² 0.5, it's okay. So then we can tune the chronology, because you know based on this ratio, and then yeah, so we have done the chronology. I'm not going into the method. If you need the paper, so in my case I did not use, but people use this. So there are some algorithm, and then there are probably Fanenda, are you going to teach for tomorrow or today? So I can give you this algorithm. It's written on the MATLAB. You can also use this for the sediment code. Okay, now boron, coming to the boron. Yeah, so this is a theory how boron actually works. So in seawater, boron exists two ions, borate and boric acid, and then their ionic species distribution is somewhere like this, 80% and 20%. So this is a borate and the boric acid, and you say 20%, 80%, and this distribution is critically dependent on the pH. So if you change the pH, then ionic distribution is going to change, and if you change them, then there will be a change in the isotope fraction, then there will be isotope composition. So that is the basically fundamental of this proxy. So and there is an empirical relation between the pH and this boron isotope composition. So okay, again I am repeating. This is a fundamental. So boron exists in two forms, boric acid and borate in the ocean, and that ionic distribution is dependent on the pH. If you change the pH, the species distribution will be changed, and then there will be a change in the isotope composition. So that change in the isotope composition is related to again pH. So you have an empirical relation between the pH and then boron isotope composition. So this borate, basically you can measure the calcium carbonate, the corals or forams or any for that matter calcium carbonate cells. Then you can, so this is a seawater value borate. So basically in which you will measure, and this is a dissociation constant people have measured theoretically, also determined, and as well as lab people have measured what will be the dissociation constant, and you put that number. If you measure the boron isotopes and corals and forams, then you can get the pH. So that is simple. Yeah. So for foram, people have used boron. Yeah. Okay. Now I'm going to the next sample. This is our lab. Okay. Okay. So this instrument will measure boron isotope, MCICPMS. We also measure some other isotopes. Okay. So how for coral, how we do? We cut the, if you have, so this was not done as a, let's say some, there are two ways you can do. You can also take some light coral, but that will give the shorter record. But if you have to go for deep record, it's a long record, then you can pour it along the growth axis. So if you have a chance, so in my case, I was unfortunate not to get that core. So it's a chunk. And then I got along the Proxies, polish it, X-ray it, and I got the chronology. Then we did the subsampling to measure the boron isotope in those samples. Now this is our lab where we do all the chemistry, and boron, hell amount of work you have to do the chemistry to extract the boron from the corals. Two ways to do the separation boron from the samples. One is you can do the column chromatography, by which like other isotopes. Then you can extract the boron from the carbonate samples. Other way, what you can do, you can boric acid actually in acidic medium evaporates. So you can do the microsublimation. So and then you can purify the boron, you can extract the boron from the samples, and then you can measure boron. One of my students, he actually did his PhD on boron isotope. Now he's working in Cambridge as a postdoc, and then measuring boron there. Okay, so these are the protocol. I'm not getting into the details. I will give the slides, so no worry. So one of the challenges that we took, actually, there was, if you see the boron isotope or boron isotope derived pH record, to understand the trend of the ocean acidification with the rise of atmospheric CO2, there are records available from the Pacific and then from the Atlantic, no record from the Indian Ocean. So this is our first record that we have given, the pH record, and then we measure the boron isotope, how it looked. And then, so coming to the corals, so coral, the equation already I have shown. So this value, seawater value is 39.6. You can give here. This is a coral delta, so you have to measure this one. And then this Kb is also again depend on the temperature. But in this case, we knew the temperature, so directly we calculated how much the Kb. And then finally, we calculated the pH of the calcifying fluid. It is not the pH of the seawater. So the pH we boron isotope we measured in coral, that gives the pH of the calcifying fluid, at which actually calcium carbonate got incorporated and deposited. It's not the actual seawater value. Then in order to get that seawater value, then we have to compute. So and then depending on the species, you have different offset. So we use it for the chlorides. They're one of the species. There are many species. If you do it, then you will see that this kind of a. So basically, if you have seawater pH, you will get this correlation. You have to measure this from this, so from boron isotope, and then you will get the seawater pH, and this is our reconstruction.
So
based on
someone
the
has already calculated the offset, so you've done that.
No, these are based on the experimental study, already done. Okay, so now pH, no, and then we, so I'm not getting into the results, so which is not important for you, so which we publish in JGR. Basically, we did not see any trend. We are expecting that with the rise of atmospheric CO2, we should expect the ocean acidification trend in the ocean, but in Arabian Sea, which have been observed in many parts of the ocean, but not in the Arabian Sea. Because if you see, we have a large variability in the pH, and that large variability is actually masking the long-term trend. So you have a slight change 0.1 or let's say 0.05, but you have a variability of 0.5 unit. So that is actually masking the long-term trend. That is one. So we did not observe. So our pH trend is actually controlled by the large variability. And second thing, but we observe that there is a relation with the end source. So basically, upwelling, there is a few hundred meter below, there is a pH, high pH water. So if you have a strong upwelling, you can bring low pH water and you can change the pH drastically. So which is happening in the Arabian Sea. So the oceanic internal processes is actually controlling the variability, not that your long-term pH trend. So that is why we could see that. Now, okay, similarly for the foraminifera, this equation, everything is same. The equation is here is different. Then you can calculate the pH. Okay, now, but then in that case, then as I said, the dissociation constant again depend on the temperature. Then, if you want to reconstruct the pH or PCO2 based on the foraminifera record, then you have to have this record. because your dissociation constant in the equation is dependent on the also temperature. So you have to know the temperature. And then there are empirical relation. People use this for a particular species. There are many species. Then you can calculate the SST. Let's say if you measure magnesium by calcium in this, you can compute based on that. But again, you need a good calibration equation, which is available for the Pacific Atlantic, but not for the Indian Ocean. But sometimes we borrow those equations, we compute. We need equation from the Indian Ocean. And then you can calculate that this is magnesium by calcium, so temperature and then salinity. Okay, now finally you can determine the pH, and then pH. If you know the pH, then you can also reconstruct the PCO2 of the ocean. So PCO2, so pH. If you surface ocean pH, then you can also calculate the pH. So in a carbonate system parameter, there are 6 parameters. The total alkalinity, DIC, carbonate, bicarbonate. Yeah, so like that, total 6 parameters. So if you know any of the 3 parameters, you can calculate any of the parameters. So then in this case, we know the carbonate, bicarbonate, all these things we know. Then finally, we can also calculate what is the PCO2. So PCO2, if you know the ocean surface, and we know the atmospheric CO2 from somewhere else, past record. Let's say you want to reconstruct that how ocean was, Ravi Bhushan showed in some slide that Bay of Bengal acted as a sink, Arabian Sea acted as a source. And do you know that based on these things, we can do that in the past, let's say thousands of years ago, how ocean acted as a past source or sink based on this more isotope record. So if you know the pH, then you can calculate the PCO2 of the surface of the ocean. Then you have atmospheric CO2. How do you know that? From the ice core. Then you have past atmosphere CO2, we know from the ice core. We know the surface ocean PCO2 from the proxy record. If you subtract number, if it is negative, it's that particular region acting as a sink. If it is positive, means ocean contributing more than as a source. So given location, given time, back in time, you can calculate, now you can estimate how much CO2 degassing, ocean acted as a source or sink. This information based on this you can determine. Okay, I will stop this here because I have taken time. I don't know how much. I'm not going into the details, but okay. These two I promise. Is that okay? Or
so we'll actually we are compiling the even PPTs as well as the documents, the papers and all, which all the speakers are citing and referring. So we would be actually what we do, we collect everything and send you the link, and we'll make a drive and send you all the participants. So even the presentations are also, videos are available on IITM YouTube channel. So anytime in future also you can just refer the if you like sometimes you miss.
Let me just half minute I can say. Actually, this is a paper published in Nature Geoscience 2K. If you anybody knows that, and then it's a compilation of all the proxy records so far measured until 2017. Ice core, pollen, everything. So you should have, and subsequently, next. Yes. So yeah. So this paper you should see. Actually, there are all the compilations of all the proxy records are there. So if you want to play with that, all the records, and then for let's say for a given location, you are reconstructing something. So you can also see nearby what are the records available, proxy records.
IIT records are also in this.
It's there in our ice core records. So this is very good compilation, and then it's a thousands of parameter proxy measures. So you should have this, and you should read these papers.
Okay, any quick question because we are running out of time.
Any question, anything? Personally, you can also write me anything because time was very 2 archives, ice core and coral, so I had to run through.
We have to ambitious anything.
So I couldn't spend much time on it.
Thank you. So next we have Dr. Praveen Mishra. He's from Western University of Jammu, and it has everything. It has everything. Whatever temperature you think is there.
Hello.
थोड़ा सा ज्यादा elaborate कर सकते हैं।
Hello. How to switch off this?
Right, you can just
Yeah, so good afternoon, everyone. I'm Praveen. So now coming to from ocean, we are again coming to the continental records, right? And there is pointer. This is next. This is next. So I have to press it, right? No. Okay. So in this talk, I'll be talking about lake sediment and how do we approach while working with the lake sediment for climate reconstruction, right? And in this case, I'll mostly talking about the approach, especially the preliminary approach and the field approach. And because since yesterday, you've been continuously listening about different proxies, like what kind of proxy we can utilize to understand the past climate variability, and how do we use the chronology? How do we use the chronology to understand the temporal distribution of different sediment layers or the different laminations in ice cores, in sediment layers, etc. Right? So in this talk, I'll use different examples. I'll try to explain you different case studies which can help you to understand the approach while working with the lake sediments, right? But yeah, so this is just a basic slide which gives you information about different climate variability in Indian subcontinent, and you already know that in Indian subcontinent, this because of this this climate variability, it has a direct or indirect influence on the agriculture productivity, right? And the agriculture sector has a huge influence on the Indian economy as well. So that's why it is very important to understand the causes of these climatic variability, right? And several scientists have also working on to understand the climate variability and to understand these forcing factors. And what they found that in the coming future, there will be increase in this kind of extreme climate variability, and also there will be a huge spatio-temporal variability in the precipitation patterns in the Indian subcontinent. Right. For example, like in 2013, we have seen there is a extremely high precipitation condition in Uttarakhand, right, which caused a damage and loss of thousands of people. So these records are these kind of studies are mostly focusing on using the instrumental record, right? So based on the time resolution, based on the objective, there are basically three type of climatic studies. One, where people use different climate models to understand what will happen in the future. Like for example, if CO2 will increase, then what will happen after 50 years? What will happen after 100 years or something like that? And some people are working with the modern climatic condition, and they use different instrumental records. But apart from these two, some of the scientists, they are working with the record which is not recorded in the instrumental, and that means they wanted to understand the past boundary condition which is not recorded, which we don't have any information about, right? So, and these paleoclimatic studies, scientists are working with the different archives. And you might have already know that there are different kind of archives, for example, speleothems, tree rings, lake sediments, marine sediments, sediment profiles, etc. So these kind of this past climatic variability or paleoclimatic study, you study using a different archives. The instrumental record you study using like different satellite data or different weather stations, and you can also do some seasonal parameter to understand the modern condition of a lake basin, right? And once you have all these information, once you have
No, they.
Home testing or all.
क्या bomb testing?
I know. It's not bomb.
Some testing.
Okay, so what we generate, what kind of data we generate by using these archives or maybe the instrumental data, we give these information to the climate modeler, and they try to understand the future climate variability and their forcing factor, right? So in this presentation, I'll be only talking about the lake sediments and their approach. So first of all, why lake is very important? Because these lake sediments or the lake basins are available all over India. If we are talking about in terms of Indian subcontinent, then these lake sediments or the lake basins are present everywhere in all geological terrains and all climatic regimes, right? For example, in Himalayan you will find so many lakes, central India, and also there are in point of like in terms of their origin, there are different types of lakes as well. For example, there are some tectonic lakes, there are some glacial lakes, and fluvial lake, coastal lakes. So you can just focus according to your objective, and then you can do paleoclimatic study. But there is a problem with the lake sediments. Why? Because you have seen speleothem records, right? You have seen tree ring records, but as compared to tree rings and speleothem records, it is highly difficult to get the annually resolved time series in lake sediments, especially in terms of Indian subcontinent. Because I've been working since last 10 years, 10 to 11 years, but I've never seen a VAR sequence in my lake records, right? And there is also a problem with this. Sometimes there is also a problem with the chronological uncertainties. They are also associated with the lake record. And since this is the basic, this chronology, the development of a chronology is the basic of a paleoclimatic study. If you don't have a better chronology, then it is very difficult to understand the climatic variability or understand to correlate this information with any forcing factors, right? And most important is there is a complex interaction between the internal and the external factors. So internal factor is the whatever the component is related with the lake water mixing, the physical chemical conditioning within the lake. The external factor is the solar insolation, human impact, volcanic activity. So there is always a continuous interaction between all these information, all these points. And because of this, they affect the sediment composition. And once they affect the sediment composition, then accordingly your interpretation will also be changed. So your first objective is to just decouple these information, like what is the dominant factor which affecting this lake sediment composition, right? So while working with the lake sediments, broadly, if you're talking about it broadly, there is three different approaches. One is the field approach, lab and the proxy calibration, and the climatic reconstruction. So in the field approach, from where you need to take the sample, what kind of samples you need to collect from the lake or from the catchment area, and also once you have the samples, then how do you calibrate the proxies according to the modern day conditions? And once you have this information, then based on this information, you can able to reconstruct the past climatic variability. Because what kind of proxies you will use, that is depending on your modern investigation. Without that, it is not possible to do the paleoclimatic reconstruction, right? Because there are so many papers you will find it in all over the world, where what people usually do, they just go in the field, they collect a core sequence, and they do their analysis and they reconstruct the climatic variability in that particular region. But this is not the correct way by approaching with any lake basins, right? So this is the diagrammatic picture of a lake, where you can see that this is the catchment area from where all the sediments are coming into the lake basins. And these catchment is directly, indirectly influenced by temperature, precipitation, and energy budget, the precipitation seasonality, pattern of precipitation. If there is a huge rainfall, that means there will be more sediments will coming into the lake basin. If there will be a less precipitation, accordingly you will get less sediment into the lake basins, right? And whatever sediments you are getting in the lake basin, that also depends on the geology of that particular catchment, right? So that means you need all this information before going to reconstruct the climatic variability. So in this diagram, mainly I'll be, or rather in this talk, I'll be focusing on 3 different components, that is water, sediment, and vegetation, right? You need to focus on vegetation, you need to focus on sediments, you need to focus on water. And because whatever changes you will get in the lake, they are directly or indirectly depending on the climatic variability in this particular region, right? And once you analyze these components, then you need to generate a different kind of data set in terms of proxies. So what kind of proxy you are using, that is depending on what type. So that depends on what type of samples you are using, right? And these proxies are nothing but these are just the tools. Like if you want to study any kind of scientific or if you want to perform any scientific study, then you need a certain kind of tools, right? So these tools are preserved naturally in a different sediment, in form of different sediment layer, in form of different laminations, and we use these proxies and try to understand the factors which are affecting these 3 components, right? Now, you go in the field, or for example, you have selected a lake basin, then there is a proper sequence, like how do you approach in the field. So this is the first one, is the preliminary investigation of while working with the lake sediment. So this includes the lake location, to understand the catchment geology, to understand whether basin is closed or whether basin is open, then the human impact, how much the extent of human influence in the lake basin, and the meteorological condition of this particular lake basin, right? Now the second approach is the field investigation. So you have this information, you already have this information, and based on this information, you go into the second step. So in the field investigation, what you need to understand is the geomorphological, and you also need to do the geomorphological investigation of that particular region, like different drainage patterns, because lake is a basin-like structure, right? There are so many sediments are coming, different sediments are coming into the lake basin through different drainage pattern. So you need to understand the drainage pattern in the lake. You also need to understand the basic morphology of the lake. There is a relation between catchment area and the lake area, also very important, because if there is a huge catchment and very small small lake basin, then in that case there might be chance that you will get very high sedimentation rate in that particular lake basin, right? So all this information you need to understand while during the field investigation. Now the third point is to sample collection. So you already have this information, you already have the information until here. Then based on this information, you need to collect the samples. You need to focus on the specific samples, whether you are focusing on the vegetation samples, whether you are focusing on sediment samples, whether you are focusing on the water samples. Now you have collected the sediment samples, or collected the different samples, and now the last step in the field investigation is the seasonal measurement in the lake. Seasonal measurement in terms of different type of sediments in different seasons, or how the lake is behaving in different seasons. I mean, the water parameter, how the water parameter is changing in different seasons, right? So, I'll discuss this later. And once you do the field investigation, once you do all the steps, then the next step is the core opening, because in core means the sediment different. You have collected different sediment from the lake. Now you send the sample for the dating, and afterwards you send the sample for the different proxy analysis depending on your objective. So this is the common step people used to usually do these kind of steps. And once you have the information, then you interpret data according to your like whatever information you are getting from the proxy data set, then you interpret your climatic condition. So the common practice is this: people do this thing and they directly reconstruct the past climatic variable, right? But the most important thing is you already have this information. You already have a preliminary investigation, field investigation, lab to the interpretation, and they interpret your data in terms of a modern environmental condition. You first of all you need to calibrate the proxy in terms of a modern day environmental condition, because you need some kind of reference, right? Because in the past, if you are saying suppose aluminum is increasing, then you need a certain kind of reference, like aluminum is increasing with respect to present, right? Or how the certain kind of proxy is behaving in present day condition. Then based on these present day condition, you need to understand the past climatic variability, right? So now coming to the preliminary investigation, as I said, the first important one is the location of the lake, right? So location of the lake is very important. The origin of the lake is very important, and also for example, you are selecting a lake from northwestern Himalaya, which is influenced by both Indian summer monsoon zone and also the westerlies, right? So this kind of lake is very ideal to understand the past climatic variability in terms of ISM and the westerlies moisture sources. Also, if you are focusing a lake from the southern India, which is influenced by both southwestern monsoon and northeastern monsoon, then it is also very important to understand the past climatic variability in terms of the northeastern monsoon and southwest monsoon. So that is why it is very important to focus on the location of the lake, from where we are selecting the lake, right? Next point is the geology of the catchment. So like I said, whatever sediment is coming into the lake basin is a cumulative response of the catchment and also the lake's internal processes. So whatever sediment is coming into the lake is contributed from lake catchment, right? So that is why it's also very important to understand the lake catchment. So what we usually do, we also collect the samples from the lake catchment as well. We also collect the sample. We also collect the rock samples. We also collect the sediment samples. If there is a vegetation sample, we also collect the vegetation sample, water sample from the catchment itself, so that we know, okay, what kind of material is coming into the lake basin, right? Now the third point is so this is just an example of a Somorelli Lake. This is situated in the northwestern Himalayan region. Here you can see the variable geology in this particular region, right? So these are the carbonate rocks and then carbonaceous cysts. So the geology of this lake is highly complex. It's not a single type of rock. You won't get a single type of rock, and there are a huge amount of different drainage pattern is also coming into the lake basin. So that's why it is very important to understand the geology of the area, because like suppose you have collected the lake sediment core from the center point, right? And there is a drainage is coming into the lake, so there might be chance sediment coming from this place, sediment coming from this place, this stream can also contribute in this particular part of the basin. So it is very important, first of all, to know the geology of this particular lake catchment, right? Now, like yesterday, Professor Sushma also said, the lake should be closed. It's very important the lake should be closed, because if lake is open, then all your signal will be lost. Whatever sediments is coming into the lake, they will get lost easily when there will be an outlet, when there will be a significant outlet, right? So this is the fourth point: the extent of human impact in the catchment in the lake basin. So humans influence this lake basin in different ways, right? I'll send you all these papers, whatever paper I have mentioned in this presentation. I'll send you all the details to Naveen, and then you can just distribute it to me, right? So humans influence this lake in different ways, right? In terms of they contribute different pollutants, and they also modify the catchment hydrology. They also modify the catchment geology as well, or not directly the geology, but they also modify the catchment morphology, right? So accordingly, once they will, for example, like if they'll grow different plants, right? Then what will happen after some point of time? This material will come into the lake, right? If there will be a deforestation that also affect the surface characteristics, and accordingly you'll get different kind of segments, right? So this is also very important to understand, like extent of human impact, how intensified extent of human influence is you are recording in the lake, in particular lake basin, right? And also, this is the meteorological condition is very important, like how much is the contribution of southwest monsoon or different kind of moisture pattern in the lake basin. So I usually use these two websites. One is a TRMM, and the another one is a climate research unit. With the help of this, you can able to understand, or you can calculate the precipitation pattern in any particular region, right? So this is the another software you can able to use it. It's a high split. All these plots are prepared by a high split software. You can able to understand different moisture source in the region. So accordingly, you can just change the different time periods and then origin of this moisture source, and accordingly, this will give you information about like from where to where this moisture is coming into this particular zone. So all this information is nothing but just this information will give you a basic information, basic idea about this moisture pattern, basic idea about the climatic condition in this particular region, so that you can able to correlate with the past climatic variability. Right? Now we already have a preliminary investigation. We already done the preliminary investigation. Now coming to the field investigation. So the geomorphology. So to understand the geomorphology of the region, first of all, you need to, like I said, you need to understand how much is the drainage pattern in this particular region, the slope of the catchment. Because if you have suppose higher slope from this region and you have a drainage pattern, then there might be chance you will get a different kind of sediments in this particular region, right? And then so it is very important to understand at least these kind of geomorphological structures in the catchment. And also you can also, if you are using some instrument, for example bathymetric echo sounder, then you can also able to understand the basic morphology of the lake. So this is an example from Somareli Lake. Here you can see that this is the deepest part. This is the deepest part of the lake. This is actually 105 meters, and this is the most shallowest part. And in the northeastern part, you can able to see there is a terraces, right? This information for getting this kind of information, you need a certain kind of instrument or certain kind of basic investigation in that region. So we have also correlated these terraces with the field data, and we also found two level of terraces in the catchment, right? So this is another example from Lonar Lake in northeastern part. Yeah, this is the northeastern part. There is an alluvial fan in the region. So if you collect the sediment, if you collect the core sediment from here, then there might be chance you'll get a different kind of characteristic as compared if you are collecting the sediment from here, because in the deepest part of the basin you'll get a homogeneous sediment from all over the shore. But if you are collecting the sediment from near this alluvial fan, there might be chance that either you will get some slumping and different or disturbed sediment in near the alluvial fan, right? So these are the instruments we used to understand the basic morphology. This is from Yeah, this is from Somorari. This is from there is a Chinese lake Binghu, and this is from Renika Lake in Himachal Pradesh. So we have done this bathymetry echo sounding of this lake, and because before this sounding, it was reported that the maximum depth of Somorari is around 75 meters. Right. So we done this bathymetry echo sounding, and we found that the maximum depth was 105 meters. So it's completely changed.
Okay, can I just ask?
Yeah.
If you don't mind? I understand even those terraces are submerged.
Yeah.
Right? How did knowing that there are terraces there influence your interpretation?
No, actually, this terraces give you information about like there was some past time, lake level fluctuation. So this information we have correlated with our like yesterday Professor Shukma showed there are two sediment core we have collected, right? And this when we compare these two sediment core, then based on this comparison we can able to say that okay, there was past lake level fluctuation. So we have just correlated it. There was no this is just a supporting evidence, nothing else. Because I've also used like I said there was this alluvial fan, if you can able to see that this one, right? So it was a two level of alluvial fan. So this information will also give you like I mean this kind of information also give you some like there was some lake level fluctuation or something. So it is not direct evidence, but it's just a corroborative evidence. Yeah. So in the lake morphology, like these three things are very important: water depth, lake size, and the watershed area. Watershed area, or you can say that the area between the relation between the lake size area and the catchment area, right? So, for example, this is a diagrammatic picture of lake. Here you can see that this is the maximum depth. So, in the maximum depth, why I am trying to push to collect the samples only from the deepest part for the climate reconstruction, because if you collect the sediments from somewhere here, then there might be chance this region is influenced only by this part and not by this part, right? And if you're collecting the sample from here, it's the same thing. So that's why we always try to collect the sample from the deepest part, so that you will get the homogeneous contribution from all over the shores, right? So this is just a bathymetry of some lake, and this FL is the fetch length, is the maximum length of the lake, and this fetch length and the relative and the water depth also defines the distribution of a sediment at the lake bottom, right? For example, this is a very shallow lake, right? If wind moves from this place to this place, what will happen? This will also move water, right? Because of this wave action, this also moves water, and because of this. Because this lake is very shallow, so this might affect the sediment characteristic of the surface. So you will get mixed sediment. If there is a deeper lake, then this kind of then in that case you will get a very good quality of sediment, right, at the bottom part. And this is just area between here. I've just like use the catchment area and the lake area from Shiloi Lake, and here you can see that the relation between the catchment area and the lake area is very important to understand like what kind of sediment, how much of the sediment is coming into the lake, right? So based on different relation, based on this water depth, lake size, watershed, and there are different ratios have been already proposed. You can also use in different ways, and all these ratios and all this information I have just compiled from this paper. So I'll just send it to Naveen. And now coming to the so this information was about the bathymetric echo sounder, right? So there is another way also you can understand the bottom of the or the morphology of the lake bottom. So I think in last 2018 or 2017 we did a fieldwork near Pune. We selected two lake basins. One is Lake Matwali. Is relatively drier area, and the Lake Indra Bazar is relatively situated in the wetter region. So one of our collaborator, he has done some seismic investigation of this lake, and based on this seismic investigation, we have selected a point from where we can collect the core. In echo sounder, you will only get the morphology of the base, right? But in seismic investigation, you will get what is present beneath the surface. So this will give you information about the type of different layering in that particular lake basins, right? So there is also another method people they use. It's a ground penetrating radar. It's also working in this almost the same principle. It's also give you information about the bottom morphology of the lake basin, right? So now we know the morphology of the lake basins. Now we need to collect the samples. So if you remember this plot where I have just focused vegetation, water, and sediment samples, and we need to understand different proxy distribution. So we use this kind of instrument to collect the samples. This is for gap sampling. This is also box scoring. This is just a video of short coring. And now just come to the graph sampling, right? So graph sampling, if you are getting low resolution of a record, then you can able to collect the samples. Then it would be really nice to collect the graph samples. But the most important thing in graph sampling is to collect. If you are focusing on any lake basin, then you need to focus on homogeneously. You need to collect the samples. It's not like you just focus on the shore region and interpret accordingly. Like, okay, in this particular lake basin, this certain proxy, for example, grain size is behaving like this. So here I'm just giving you two examples where I have used around 35 samples, and I have used the spatial distribution of this proxy, and I've just removed some of the data points. Here you can see that the spatial distribution of proxy is completely changed. So when the spatial distribution of proxy will change, then accordingly your interpretation will also change, right? So that's why the most important thing in graph sampling is to just collect the samples homogeneously from the whole lake basins, right? From different water depth. So this is the example from Ansar Lake in Kashmir. We have collected multiple short cores from the lake basins, and here you can see that we have focused on the core from the deepest part of the lake, that is 8R9. Interestingly, all these cores, we collected 13 cores from this lake basin, and all these cores lithologically they are exactly the same. Okay, there is the minor differences in the lithological unit, but the characteristic of each lithology is exactly the same. But so in the deepest part here also you can see we have found 4 different litho units. So we have just focused on the litho in this particular core basin. So all this information, whatever information we get it from this morphological structure, we have utilized to select the core for a climate studies, right? Now coming to the long core, all this information I have just discussed here about shorter cores. So now coming to the longer cores, suppose we have collected 2 cores. One is from the shorter, shallower region, another from is the deeper part, right? So this is the example from the Somerari. We have collected 1 core from the shallower part, another core from the shorter, deeper part. So these are the litho units in these 2 cores. One is at 40 meter depth, another one is at 105 meter depth. So based on these relation, based on the intercomparison between these two long cores, we have reconstructed the past lake level fluctuation. Although this is not this information is not quantitatively reconstructed, but we have qualitatively reconstructed. Okay, in the past there might have been chance that lake was goes up to 7 meter. I mean, it was during the Holocene, lake level was increased up to 7 meter more, right? So if you are focusing on the long core, so what different industries or what people try to use to do while collecting the long cores from the lake bottom, we usually do a multiple parallel. We collect parallel cores from the same bottom. For example, at this place we have collected a long core, and after a few meter away from this borehole, we have again collected the long core, but from the different depth. For example, in borehole A, we have collected the sediment from 0 meter of water depth, right? From the surface, we have collected the sediment core. But in borehole B, we have collected the sediment from 0.5 meter of water from the sediment depth. So that there might be chance if there is a sample loss in this borehole, then we can recover this part from the another parallel core. And accordingly, we prepare our composite. So in paper, whatever you see in terms of a different long course, that is actually a composite core. That is not a single core, right? So now coming to the catchment sampling, and I was talking about why catchment sampling is very important, because here you can see there is no any yellow regions, right? But in the lake segment, we have found this yellow. So this yellow is nothing but it's a aragonite mineral. So this distribution, this mineral distribution itself says that in the lake we have found aragonite mineral concentration minerals, which indicates it's because of the change in the evaporative processes. 5 minutes, 10 minutes max. Right? So, so based on this information, we can able to understand, like, okay, in the lake we have found aragonite, which is the evaporative process. So based on this information, we can able to reconstruct it. We have reconstructed the past climatic variability in Sommerari. Now coming to the water and vegetation samples, like I said, all these water or vegetation has a direct or indirect influence on the climate variability. If the climate will change, this will also directly or indirectly affect vegetation in the region. This will also affect the water composition in the region. So we also collect the water samples. We also collect this vegetation samples. Now coming to the seasonal measurement. This is a sediment trap. You just need to place them at the bottom of the river, bottom of the lake, or maybe at the shallow part of the lake, so that you can able to understand what type of sediment is coming into the lake, and what type of sediment is reaching to the bottom of the lake or the maximum depth of the lake, right? So this is one of the instruments, and another instrument is to understand the physical and chemical parameters in the lake basin. So using all these instruments, you can able to seasonally, you can able to understand the seasonal behavior of different sediment characteristics in the basin, and also the water parameters. So this is nothing but this is just a modern investigation. You are focusing on all these components, and based on this component, you have just calibrated different proxies according to the change in the modern day environmental conditions, right? So you have this information. For example, in Sommerari, we have this information like aragonite. We are getting aragonite, which indicates the evaporative process in the lake basin. So now you have sediment cores. You have a long course, so you need to cut this core into two different halves. There are different processes. Either you can just directly cut the core into two halves, or maybe you can just directly extrude all the sediments without cutting the core, right? So these two processes are very common. So once you have all this information, you need to document all the marker layers, all the different kind of information what you can visually observe. If you have these instruments, for example, micros XRF or something like that, then you can able to understand the elemental concentration of the sediments. And because these information will finally will help you to make a composite of the long core, right? And once, so this is the final step. You have all the sediment cores. Now you send the sample for the dating, then also for a different proxy analysis. And when you combine the calibration part and this proxy data, then you can able to understand the past climatic reconstruction in the region. So I'm not going to discuss this thing because this have been already discussed by several teams. So these are just a proxy information like biomarkers, the grain size. One thing which I would like to tell you about, this plot looks very complex, right? Why? Because each proxy is directly or indirectly influenced by another proxy as well, right? So that's why it is very important to focus on multi-proxy approach. If you are only focusing on single proxy, there might be chance there is some error associated with that particular proxies. then your whole interpretation will also depending on that particular process, right? So that's why it is very important to understand the interrelationship between all the processes together. Now, in summary, the whole approach is divided into two parts, basically preliminary study and the field study, and then we open the sediments, and then we do the proxy analysis, and we do the reconstruction. And once we have all the information, we provide this kind of information to the climate modeler, and they can able to understand what will happen in the future and what is the current condition of the climate. So thank you very much. If you have any questions, please.
Any questions?
Maybe lunchtime.
Everybody's hungry, I think. Yeah, we are between food and
Maybe lunch maybe.
Glacial lakes. Okay, so if the lake is located somewhere about
And how you will manage to collect the sample, because at that particular altitude to carry the.
See, actually, in a glacier lake, the problem is the main problem is the logistics.
So it's like 87 meters.
hello. So you there is a request, please quickly so then the bus is ready. So all of you go to Isaac for the okay.
Yes, sir. You can lock this out.